I met breakfast this morning. A lot of people from different countries here.
Several companies, including the company. It's a premier organization in manufacturing. There's a pretty company that very we have done extensive Asia, Yemen, Asia, Turkey, Sudan, Afghanistan, yes.
Bismillah ar-Rahman ar-Rahim. Welcome all the participants to today's event. Before we formally start with the inaugural session, I would like to welcome our distinguished guests for the inaugural session. Thank you so much, our chief guest from Mauritania, Professor Dr. Ahmed Al-Mouna, our guest of honor, Mr. Imtiaz Ratkar. Thank you so much, sir. We have Excellency Professor Dr. Muhammad Iqbal Chaudhry, Coordinator General Comstech. We also have from Pakistan Vacuum Society, Mr. Tariq Sattar, Dr. Javed Bhatti, and our resource person from the US who will be delivering the large chunk of this workshop, Professor John Grant. Thank you so much for being here, sir. We would like to formally begin the inaugural session with the recitation of the Holy Quran, for which I would like to invite Mr. Costa.
أعوذ بالله من الشيطان الرجيم بسم الله الرحمن الرحيم خلق الإنسان من صلصال كالفخار وخلق الجن من مارج من نار فبأي آلاء ربكما تكذبان رب المشرقين ورب المغربين فبأي آلاء ربكما تكذبان آمنت بالله صدق الله العظيم.
Jazakallah. First off, I would like to invite Coordinator Pakistan Vacuum Society, Mr. Tariq Sattar, to introduce the audience regarding today's workshop. Please, sir.
نحمده ونصلي على رسول الكريم أما بعد فأعوذ بالله من الشيطان الرجيم بسم الله الرحمن الرحيم. His Excellency Dr. Ahmed Al-Mouna, Director General, National Agency for Scientific Research and Innovation, Mauritania. Guest of honor, Mr. Imtiaz Ahmed Ratkar, Chairman, Ratkar Group of Industry, Islamabad. Professor Dr. John T. Grant, Chair, IUST Applied Surface Science Division. Professor Dr. Muhammad Iqbal Chaudhry, Mustafa Peace be upon him, Prize Laureate, Hilal Imtiaz, Tar Imtiaz, and Coordinator General Comstech, Dr. Javed Hassan Bhatti, President Pakistan Vacuum Society. Ladies and gentlemen, esteemed members of Pakistan Vacuum Society, distinguished guests, and fellow scientists, Assalamu alaikum and good morning. In this fine morning, it is great pleasure for me to welcome you all on behalf of the organizing committee of International Technical Training Course on Vacuum Application in Applied Surface Science 2023. I would like to extend my sincere thanks to Honorable Chief Guest, Dr. Ahmed Al-Muna, for accepting our invitation to inaugurate this course. I am extremely grateful to our guest of honor, Mr. Imtiaz Ahmed Raskar, Chairman, Raskar Group of Industries, for gracing this occasion with his presence. I am also grateful to extend my wholehearted thanks to Professor Dr. John T. Grant, Chair IUSTA, Applied Surface Science Division, for accepting our invitation as a main resource person for this course. I am also grateful and extend my special thanks to Professor Dr. M. Iqbal Chaudhary, Coordinator General Comstech, who provided us OIC Comstech platform for this event and full support to organize this event. I am grateful to all organizers of PBS and Comstech and faculty members whose spirit, coordinated efforts, mutual cooperation, and common understanding has taken this event to a successful launch. All this praise goes to Allah, the most gracious and most merciful, whose blessing helped us to undertake this event. Sir, besides foreign participants from Malaysia, Indonesia, Mauritania, Kazakhstan, Yemen, Cameroon, a large participants from local industry, universities, and our R&D organizations are here to attend this course. Technological advancement is undoubtedly an issue of great importance for the progress of our country. Ladies and gentlemen, today the world around us is changing in ways that could have not been imagined yesterday. Science and technology has brought a revolution in the structure of our society. The vacuum and surface technologists in today's world acts as full partner in all interdisciplinary teams of experts. The rapid advance in science and technology and the increasing use of vacuum in various research and industrial applications world over give rise to a continuing demand for education and research in vacuum technology and surface sciences. The application of vacuum technology and surface sciences in the modern industrial world are countless. Equipment and processes in most of the industrial sector like defense, medical, aerospace, electronics, automotive, etc. use vacuum technology as an essential tool. From an economic point of view, the industrial applications are much more important for vacuum industry than its application in physics research. According to a survey of Engineering Federation in Europe, the United States and Japan, about 40% of the sale of vacuum-related equipment of companies in these regions go into semiconductor industry. This is by far the largest segment of the vacuum technology market. However, the significance of vacuum technique for physical research has not dropped at all. Hardly any physical experiment in academic or research sector is conducted outside of vacuum environment. Whenever vacuum technology comes into action, surface sciences plays an important role in all areas of application, from high-tech research to everyday use in life. For example, freeze drying or vacuum packaging of food, coating of lemonade bottles to reduce the loss of carbon dioxide gas, coating of architectural glass to reduce the loss of thermal energy, material science, surface analysis, and many more. Sir, in this course, vacuum application and techniques related to surface sciences will be covered, like thin film deposition, surface modification, surface analysis techniques, surface characterization and testing. And various techniques will be discussed in detail, like Auger electron spectroscopy, X-ray, photoelectron spectroscopy, electron spectroscopy for chemical analysis, secondary ion mass spectroscopy, sputtered neutral mass spectroscopy, total reflection, X-ray fluorescence, scanning probe microscopy, etc. Overall, vacuum technology is a fundamental tool in applied surface sciences, allowing researchers and engineers to control, manipulate, and analyze the properties of materials at the nanoscale, which has far-reaching implications in various industries and scientific disciplines. Dear participants, Pakistan Vacuum Society has been established to overcome shortcomings in these areas in understanding and short-sightedness in visualizing the importance. This society has always supported networking among academic and industrial professionals involved in diversity of disciplines. Since its emergence in 1997, PVS has organized more than 15 national and international events. This 3-day technical training course has been divided into two parts. First part consists of presentations, which will be held in the morning, whereas the afternoon sessions have been arranged for the practical demonstration and hands-on training. On the third day of technical sessions, there will be a concluding session where distinguished participants will be invited to express their views and comments on course deliberations. Sir, to relax the participants and to provide some change from boring and dry technical discussions, the PVS has arranged a dinner and culture show in tomorrow evening. Once again, I welcome you all to PVS International Technical Training Course. Thank you very much.
Thank you so much, sir, for providing an insight to this workshop and what will be covered during the 3 days. Up next, to give a brief regarding Pakistan Vacuum Society, what they are and what they are working on, I would like to invite the president of Pakistan Vacuum Society, Dr. Javed Bhatti. Please, sir.
Bismillahirrahmanirrahim. His Excellency, Chief Guest, Dr. Ahmed Al-Manu, Director General, National Agency for Scientific Research and Innovation, Mauritania. Honorable Guest of Honor, Mr. Imtiaz Rafgar, Chairman, Rafgar Group of Industries, Professor Dr. Muhammad Iqbal Chowdhury, Coordinator General, Comstech, Professor Dr. John T. Grant, Head Applied Surface Science Division of UVista, Chaudhry Tariq Star, Senior Vice President and Course Coordinator of this event, distinguished guests, ladies and gentlemen, Assalamu alaikum and good morning. In this fine morning, it is my great pleasure to welcome you all on the occasion of the inaugural session of the International Technical Training Course and Vacuum Applications in Applied Surface Science, organized by Pakistan Vacuum Society with the collaboration of comstech Islamabad. This is the 9th International Technical Training Program undertaken by the Vacuum Society after successfully conducting 20 national and 3 international events in just 25 years of its life. This year, PVS is celebrating Silver Jubilee, and this is one of the events of Silver Jubilee celebration. This period represents our continued struggle to overcome all difficulties to achieve the objectives of the society and thus to serve the vacuum community in Pakistan. Ladies and gentlemen, Pakistan Vacuum Society serves a very different need and a much wider client base than other single discipline societies. There is prolific activity on many fronts, from the use of vacuum in science and technology to education, to educating young engineers, researchers, and technicians in the art of vacuum technology. Although PVS is continuously holding national and international technical workshops, symposia, and training courses on vacuum technology, this is the 3rd event PVS is jointly conducting with the collaboration and patronage of comstech Islamabad, thus establishing a linkage between vacuum technology and applied industrial field. I am highly indebted to Professor Dr. John T. Grant, who a year ago promised to conduct this previous technical training course in Pakistan in October 2023. He fulfilled his promise despite his cancer surgery and chemotherapy treatment last year. I am extremely thankful to Professor Don, who has come straight from Ohio to conduct this course. I am also thankful to the faculty members whose spirit and coordinated efforts have taken this event to a successful start. All this praise goes to Allah, the most gracious and most merciful, whose blessings help us to undertake this gigantic task. Ladies and gentlemen, this technical course shall provide an excellent opportunity to researchers, planners, and industrialists from Islamabad and other cities to exchange views and to adopt appropriate methodologies for incorporating correct use of vacuum techniques in their future endeavors. It will help to cope with the changing market trends as well as increasing the industrial output. This training course will go a long way in human and industrial development in the country. I would like to take this opportunity to briefly introduce the setup, functioning, and update on the progress of the Pakistan Vacuum Society. As you know, the Pakistan Vacuum Society is run by an executive council and general body. The executive council supervises the affairs as per society by rules and regulations, while the final decisions are approved by the general body of the Pakistan Vacuum Society. The day-to-day affairs are run by an elected body for a term of 3 years. PVS is a non-government, non-profit organization which promotes communication, dissemination, and knowledge, recommended practices, research, and education in the use of vacuum and other controlled environments to develop new materials, industrial processes, and devices. This society provides stimulating symposia, short courses, and educational outreach, both at the national and international level. It is run by an elected body comprising leading vacuum technologists belonging to industry and research institutions of the country. Annual membership are mostly from MCS. At present, there are over 430 life members and 35 annual members of the society. Annual members are mostly MPhil and PhD students who join this forum without any fees. This society is regularly bringing out its quarterly newsletter, Pak Vacuum, to keep its worthy members abreast of the latest developments in the field of vacuum science and technology. The main source of income of the society is membership fees and course fees and donations. At the national level, Pakistan Vacuum Society is registered with the Registrar Joint Stock Company, Islamabad. It is registered with the Pakistan Science Foundation and Pakistan Council for Science and Technology as scientific body. At the international level, it represents Pakistan as the International Union for Vacuum Science Techniques and Applications, which has 34 member societies all over the world with head office in Brussels, Belgium. UVISTA also financially supports training program as well. And other advantage of this membership is that other international research organizations are offering training programs to PVS. Up till now, over 15 PVS researchers have undertaken training abroad, ranging from 3 months to 2 years in the field of vacuum and applied areas. Three of our researchers have been awarded scholarships for PhD studies in the foreign country. Besides this, advanced literature and journals in the applied fields are pouring in free of cost. Pakistan Vacuum Society is also managing its own library, which contains product catalogs from international companies, latest books, reports, journals, and magazines related to vacuum and its applied areas. Ladies and gentlemen, one of the main endeavors of the society is the creation of a state-of-the-art and first of its kind institute named National Institute of Vacuum Science and Technology in Islamabad. This is a very big achievement of the Pakistan Vacuum Society in Pakistan. This institute has been established under generous grant and approval of Higher Education Commission. Presently, this institute has over 15 labs on various vacuum technology subjects and standards. And NOAS is conducting over 20 regular short courses and training programs throughout the year. We hope and expect NOAS will soon be able to launch the BSMS degree program and 3-year diploma courses in vacuum physics, vacuum engineering, and vacuum technology. Third, recognizing the efforts of PVS in the education sector, UVISTA has declared the appraising of National Institute of Vacuum Science and Technology at International Vacuum Institute in the world. Now, NMR should work hard to catch this opportunity with full zeal and vigor. On behalf of the PBS, I must record my thanks to various departments of the country supplying the vacuum technology equipment for demonstration and training purposes on loan for this event. I am really grateful to Dr. Ahmed Al-Manu from Mauritania for accepting our invitation and gracing this event as the chief guest, and to Mr. Imtiaz Al-Skar for gracing this event as guest of honor. I am highly thankful to Professor Dr. Muhammad Iqbal Chaudhary for generously supporting this event. Without his support, this event should have not been possible. I am also thankful to USTA and Pakistan Science Foundation for their financial support. I am also grateful to the officers and staff of comstech for managing this event in the best possible manner. My special thanks and appreciation go to Chaudhary Tariq Star, coordinator of this course, and his team, whose visionary leadership and enthusiastic moral and material support has made this event a great start. I would like to express my personal gratitude to the organizing committee and support staff of PBS, who took very keen interest in the affairs of the society and made this event a success. In the end, I express my thanks to all of you for coming here and joining this ceremony. Thank you, and I hope hopefully you will take full benefit of this program. You can discuss your problems freely with our experts during training and even after this program. Thank you very much.
Thank you so much, sir, for your remarks. Up next, I would like to invite the Coordinator General Comstech, His Excellency Professor Dr. Muhammad Iqbal Chaudhary, for his welcome address.
Bismillahirrahmanirrahim. Assalamu alaikum, ladies and gentlemen, professionals of very important technology. And of course, I'm absolutely delighted to welcome my dear brother, Professor Dr. Ahmed Al-Manu. See, I traveled far and wide, and during my tenure, I traveled to some of the most exotic places for me in West Africa and Sahel region. And I consider Professor Al-Manu is my biggest discovery. Wonderful person with great vision and perseverance and this inherent optimism to do something for the country. We have with us guest of honor, Professor Mr. Imtiaz Ahmed Rastagar, Chairman of Rastagar Group of Industries. Now, as you know, that this is a technology-based industry, and certainly one of the most important industries that has competed with the international industries in terms of its quality and its innovation. So we are so delighted to have you, sir. Thank you very much for coming. We also have with us very distinguished, accomplished professionals, Professor Dr. John T. Grant, representing International Union of Vacuum Science and Technology. Dr. Javed S. Bhatti, President, Pakistan Vacuum Society. Mr. Chaudhary Tariq Sattar, Course Coordinator. And distinguished guests, ladies and gentlemen, it is indeed a unique honor and a personal privilege to welcome you all to this international training workshop. You see, there were two reasons when I met with this distinguished group of people about 4 months ago. There were two reasons to accept their offer readily. One was personal, that I'm a chemist by profession, and that I am a very extensive, vigorous user of vacuum machines. from using that for drawing to analytical purposes. I use mass spectrometry, I use X-ray crystallography, and all of them are absolutely crap, nothing else, 100% useless piece of equipment without vacuum. And I must say that I've been totally convinced that vacuum science and technology is extremely important. Second is that I have this wonderful feeling that Pakistan has been the forerunner of technologies for literally decades. You know, either space technology or nuclear technology or other technologies, Pakistan has been on the right at the front, including vacuum technology, and we have really done wonderfully well in all these technologies as one of the most technologically advanced OIC member states. We unfortunately have lost some of it in last few decades, but I'm sure that we have the potential and ambience and capacity to catch it again and then excel. And there were two reasons that I readily accepted. I also requested them that this is the beginning of a very exciting collaboration between Pakistan Vacuum Society and comstech, which is responsible of building science and technology capacity. Why don't we have it internationally as well? You know, International Vacuum Society has only two OIC member states. Why not more? Why don't we create more vacuum societies in other countries, other members, OIC member states? Why don't we take this capacity of ours, where we have some of the finest expert in this technology, to the other OIC member states? Why don't we have it in Mauritania and Nouakchott for West Africa? Why don't we have it in Uganda for Central Africa? Why don't we have it in Djibouti for East Africa? So we wish to take the expertise and excellence of Pakistan to other OIC member states, showcasing Pakistan's excellence in various fields, at the same time fulfilling this mission of ours to rise together, to have development for everyone, and that to have this inter-Islamic cooperation in this very important field. So this is what I really feel our future commitment is, and that we intend to fulfill this, inshallah, as we move forward. Ladies and gentlemen, there are technological advancement that Professor Abdul Salam used to say that the difference between the developed world and developing world is not the wealth, it is knowledge, it is the technology. So if anything really distinguishes between with the developed nation is technological advancement and knowledge. And that is the name of the game. And I would like to read one very important piece of foresight exercise, which was conducted by Mackenzie's Institute. It's called Next Big Things. It's a post-industrial economies of the world in next 15 years. And the report says that 12 emerging technologies, including big data, blockchain, robotics, IoT, advanced energy storage devices, autonomous vehicle, third generation genomics, regenerative medicine, and some more, are going to be the game changer. They would drive a massive economic transformation and collectively generate over $33 trillion in next 1 decade. It is going to be very obvious that a lot of these developments are taking place in the developing world. But question is, why can't we do that in our country? You see, these technologies are not capital intensive. They are intellectual intensive. And 1.9 billion population of the Muslim world, 1 billion of them are below the age of 25 years. This is the creative potential. this tremendous pool of creativity which need to be unleashed and harnessed. And this is exactly what comstech is trying to do. Comstech is trying to build capacity in frontier science technology, and certainly vacuum technology is one of them. I'm very happy that this partnership has now emerged into a very important program, and that I looked into this line of speakers of extremely distinguished careers, each of them with a unique insight and a long experience. They are the real practitioners of this important field, and it would not be possible for this time to acknowledge each one of them, but I'm sure that they would all contribute. Eventually, what we would like to see a legacy behind, alumni of this training workshop, also a proceeding of this training workshop, and also a plan for future. This is what comstech expect from this particular workshop. Let me say a few words about comstech, which is one of the premier organizations of OIC system. It is OIC's Standing Committee for Science and Technological Cooperation, comprised of 57 ministers and chaired by the President of Pakistan and co-chaired by the Prime Minister of Pakistan. Our mandate is to promote science and technology cooperation in OIC member states. And our challenge is to develop inter-Islamic cooperation. See, we see countries developing and investing hugely in their own science and technological development. comstech real challenge is to motivate them to work with other countries and to help them to develop their S&T also. This is where we really find one of the most difficult paradigm which has to be changed, and we are trying to change it in our own humble way. comstech has initiated many programs, and as per its mandate, we have a large capacity building programs. So we have over 500 fellowship, including a large number of them for Palestinian brothers and sisters. We have country-specific programs, Yemen, Nigeria, Sudan, Somalia, and we are also in the process of establishing many institutions through the support of Islamic Development Bank and Islamic Solidarity Fund. Along with this, we also have many programs in the healthcare sector. So we are actually sending our doctors, which are some of the finest doctors in fields such as ophthalmology, histopathology, oncology, and neurocritical care to different places, not only to conduct camps, but also to build the capacity of local doctors and technicians, a very important sector of our activity. And of course, our program for Muslim minorities in non-OIC member states, a very important one. In all of this, our finest institution in OIC world called comstech Consortium of Excellence has played a very important role, because these institutions are the places where we are able to conduct many of these activities. So I wish you a very successful training course. I expect that its proceeding will be compiled and will serve as a valuable source for OIC member states. I would also request you to think really seriously and with spending a little bit more time of creating professional societies of vacuum in different member states, and then eventually to create an alliance of vacuum societies in OIC member states. I also wish to acknowledge my team at comstech, which has played a very important role under the leadership of Haris Ikram and our very valued partner, the Pakistan Vacuum Society, wonderfully motivated group of individuals, some of the finest people, and certainly people who really inspired everyone. Thank you very much. Thank you. Assalamu alaikum.
Thank you, sir, for your wonderful remarks. Next, I would like to invite the resource person for this workshop, Head Applied Surface Science Committee, Professor Dr. John Grant. Please, sir.
Well, thank you very much. Good morning, everybody. And thanks also to all those people up here. I'd like to particularly thank His Excellency, Dr. Ahmed Aluma, our guest of honor, Dr. Raskar, and Dr. Mohammed Chaudhry, the Coordinator General of Comstech, and the representatives also from the Pakistan Vacuum Society, Dr. Javed Bhatti that we have, and Tariq here, Sattar. Also, the esteemed members of the Vacuum Society of the Pakistan Vacuum Society, and also all our guests here, ladies and gentlemen. I came to Pakistan in 2010, at which time I was at Ninvast, where I gave a course there as well. And I felt so welcomed to be in Pakistan at that particular event. It was really a pleasure. And I know Dr. Bhatti has been asking me for many years to come back to Pakistan and teach another course. So I'm very happy to be here. And I hope that you will learn a lot during the course. So I just wanted to say a few words. The International Union for Vacuum Science, Technique and Applications, that's where the term UVISTA comes from that acronym. And it's a union of 33 science and technology national member societies. So we've grown a little bit in the last few years. And I was very happy this morning at breakfast to meet so many people from different countries. And most of you are sitting right here that were at breakfast. And that was especially nice to see so many of those here. And UVISTA is a very open organization. And it'd be nice to see some of these other countries also join UVISTA and participate in various activities of UVISTA. And I can say a few words here about from the slides that I have from UVISTA. UVISTA likes the representatives at different workshops and training courses to show these slides about UVISTA. And that's why I've put them in here to show you a little about UVISTA. But before I go through this, I just want to say that I was born in Australia, so maybe I have a different accent from what you might expect. Okay. I got my education in Australia, my PhD. And after I got my PhD, I went to the United States for 2 years. And then I went to the Netherlands for 2 years and worked at Philips. And at Philips, I worked in electron microscopy groups and also their surface analysis groups. And as you're aware, Philips was very involved in all kinds of vacuum technology back then as well. I mean, their name is after the light bulb. Their official name was Philips Gloeilampen, and that means light bulb, basically. And so I worked there. Then after 2 years at the Netherlands, my colleagues in the United States asked me to come back and join them and work with them. So after I left Australia, I became involved in electron spectroscopy, specifically Auger electron spectroscopy. And that's named after a Frenchman, Pierre Auger. That's why we call it Auger electron spectroscopy. When I first went to Britain to a conference back in 1971, all the Brits were calling it Auger spectroscopy. And back then also, the people in England and the French did not get on well. There were a lot of conflicts. And I don't know if it was on purpose that they called it that way, but it was supposed to be called Auger electron spectroscopy, but I'm not sure whether they realized that or not back then.
But now, of course, they all call it Auger electron spectroscopy. Relations have improved, but now the European community, maybe relations won't be so good anymore. So maybe they'll start calling it Auger spectroscopy again, I'm not sure. And then I got involved in another technique called X-ray photoelectron spectroscopy, which is the technique that I use most of the time. Ion spectroscopies are also extremely important in analyzing materials. And it's nice to have access and knowledge about these techniques. One thing I found over the years is that in working in the lab, a lot of my colleagues would come to me and ask me, John, what technique should I use to solve this particular problem? Because they didn't have a good background on different techniques. So even though you're not using electron spectroscopies or ion spectroscopies, it's very important to understand what these techniques are to help you in your research development, in your corporations, to improve products. And you can always access these analysis methods from other companies or universities to help you in your research to make better products, for example, and new products. And a lot of electronics now, that the size limits, we're getting smaller and smaller devices all the time. So surface interface thin film properties are extremely important in materials development. So the goal of my course here is really over the next 3 days to give you an introduction to these techniques so you can understand the basics of the techniques. Because if you don't understand the basic principles of them, you don't really understand what you can learn from them and look for certain pitfalls or problems with them. So you know which ones are best to use for your particular needs in your work. So that's the goal in the next 3 days, is to introduce you to these techniques and give you some examples from many areas of science and development where you can use these techniques to really learn a lot about materials properties. And these techniques are used in vacuum, which is extremely important. So, and then at the end of the course, I'm just going to talk about a couple of a few techniques that are not using vacuum, just for completeness. So as I said, I'm especially happy to be here again with my colleagues and my friends from Pakistan, and also with all of you as well during the next 3 days. So thank you very much for your kind invitation, particularly to Comstech and the Pakistan Vacuum Society for hosting me at this training course. Okay. Thank you very much.
Thank you, sir, for your remarks, and we're very happy to have you here in Pakistan to deliver this training session over the next 3 days. Moving on to the guest of
Assalamu alaikum. Honorable Chief Guest, Dr. Almuna and Dr. Grant and Dr. Iqbal Chaudhary, Javed Bhatti Saab, and Tariq Sattar, and all the distinguished guests, ladies and gentlemen. I am very honored to be here standing before you at this international technical training course, which has been organized by the Pakistan Vacuum Society. And as you have already heard, it's high level of dedication to the science of vacuum and the practice of vacuum. And I have been in business almost now 56, 57 years. And one of my businesses is in compressed air. And I have been involved with compressors and vacuum machines for quite some time. And it goes beyond business. It's like a labor of love. And each time that there is Hanover Fair, every 4 years, they bring in one sub-fair at Hanover, at the Hanover Messe, which is known as ComTech, compressors and vacuum. So my last visit there was in 2016. And when I was going around, I went to the stand for labeled areas. I think the name of the company has changed. I remember it from the old times as labeled areas. I was following this company since the 70s when they were using vacuum and deposition technologies and sputtering technologies and vacuum and different things. So just out of that old association with the name, I went on to their stand, and once they saw my card, they said, "Sir, we can't speak to you." All right? No, we can't speak to Pakistan. So when Dr. Iqbal was talking about the knowledge gap, here was one effort of somebody somewhere to control that knowledge gap. And with my association with NINVAST and Dr. Bhatti and the great amount of work which is done here in Pakistan in developing the local equipment, local technology. So I could understand that there are people, who don't want to bridge this gap, but we are distinguished people here sitting. So that is the gap and which people like you here from industry and research, and this is our effort to fill that knowledge gap. And it's not only knowledge gap, it goes beyond that equipment gap and ability to make business out of this knowledge. So it should also translate to better business and better economy. So as we gather here today, we are not just visualizing the remarkable achievements of the past, but also conducting this international technical training course for the future. The collaboration of IUVST for this international course entitled Vacuum Applications and Applied Surface Science highlights the importance of practical knowledge, innovations, solutions in vacuum technology. It is an evidence to the fact that our work extends far beyond laboratory experiments and theoretical studies, directly impacting industries, healthcare, electronics, and much more. The challenges we face in the 21st century are as diverse as they are complex, ranging from addressing environmental concerns to modern electronics, from advancing materials science to improving medical diagnostics and treatment. The role of vacuum technology in applied surface science is pivotal. The knowledge that would be shared and collaborations going to establish here will be stepping stones for the solutions that will help us tackle these challenges, create a better and more sustainable world. So let me also inform the House here that in my personal capacity and previously as Chief Executive Officer of the Engineering Development Board, I have tried to bridge this gap. And more recently, we have here, Dr. Iqbal, we have a set of high-tech industries which don't have a platform. So we realize this, and the chambers of commerce and the other societies, they don't, and the government sort of don't recognize this. But there are very high-tech pockets in Pakistan, and one of them is the aerospace sector. we have a large number of companies who feed into our defense industries, particularly into the aerospace industries. So what I managed to do was to form a small society, Pakistan Aerospace Council, under one of the non-profit which I have created. But we have now about 72 companies which are our members, and they contribute into radar, to all kinds of high-tech equipment, and some of them are exporting. Some of them we managed to connect to CERN, and they are now sub-suppliers to CERN now. And Dr. Bhatti is also one of our members there also. So there are small pockets, and like here is an effort to connect all of you with vacuum. There are other things going on, and it's also, an effort that different people in different high-tech spheres, they get together and create a situation where the economy gets better and our equipment gets better, and we can make better and more expensive exports. So before I conclude, I would like to express my deep gratitude to Pakistan Vacuum Society and Comstech for organizing such a fruitful event. I do feel pleasure to extend my special recognition to each and every one of you for your dedication and presence in this course, and of course to the organizing committee of the National Vacuum Society and Comstech for creating this event. Let us take full advantage of this, the knowledge and connections that will be developed in the coming days. I have no doubt that the ideas and innovations that will emerge from this course will lead us to transformative breakthroughs in applied science. Together, we have the power to shape the future and make the impossible possible. Thank you very much.
Thank you very much, sir. Before moving on to the speech by the chief guest, I would like to especially thank the diplomatic representatives present here, Her Excellency, Ambassador from Northern Cyprus. Thank you so much, ma'am, for being here. Also, the international participants present, I would like to inform the chief guest that we have international participation here today from Malaysia, from Indonesia, Cameroon, Ethiopia, Yemen, Ghana, Kazakhstan, and many more that are connected via Zoom as well. We have from Iran as well. So thank you to all the international participants and the diplomatic representatives for being here in the inaugural session. Now, I would like to invite the chief guest, Director General, National Agency for Scientific Research and Innovation, Mauritania, His Excellency Professor Dr. Ahmed Al-Muna, for his remarks. Please, sir.
Thank you. بسم الله الرحمن الرحيم. الصلاة والسلام على أشرف الأنبياء والمرسلين. Guest of honor, Mr. Dr. Imtiaz Rockstar, Chairman of Rockstar Group of Industries, Professor John Grant, Chair of UVista. We just told that a little bit about it. It's good. Your Excellency Professor Dr. Muhammad Iqbal Chowdhury, Coordinator General Comstech, Dr. Javid Bhatti, President of Pakistan Vacuum Society, Dr. Chowdhury Tariq Sattar, Course Coordinator, distinguished guests, ladies and gentlemen, Assalamu alaikum. Good morning to all of you. I am truly honored to be here as a chief guest for this international training course on vacuum application in applied surface science. I'm delighted to learn that Comstech and Pakistani Vacuum Society has joined effort to organize this interesting course on vacuum on vacuum application in surface science. It is very important for scientists, for technicians, for technologists, because of its widespread application and indeed for its added value to local industries and technological development. Vacuum science has played a paramount role in advancing our understanding about physical and chemical properties of surfaces. It has also enabled us to explore the properties of materials at the atomic and molecular level, leading to groundbreaking discoveries and innovations that have transformed our world. From the development of new materials to the development of existing technologies, the implication of vacuum science in applied surface science are vast and profound. So in this age of rapid technological development, vacuum applications have become increasingly vital. Vacuum innovations have modernized industries such as electronics, material science, and even space exploration. Vacuum technology is at the core of semiconductor manufacturing, where nanometer scale precision is required to produce the microchip that power our modern devices. It plays a fundamental role in creating thin film and coating that enhance the functionality and durability of product, ranging from even contact lenses to spacecraft. So furthermore, vacuum application in surface science have led to significant breakthrough in understanding and addressing environmental and energy challenges. Techniques like surface analysis and surface modification have enabled us to develop more efficient catalysts, improve energy storage system, and design advanced material for renewable energy applications. These developments are essential for a sustainable future as we strive to mitigate the impact of climate change and transition to clean energy sources. The interdisciplinarity nature of vacuum application in surface science is truly remarkable. Scientists, engineers, and researchers from diverse fields collaborate to push the boundaries of knowledge and innovation. It is through such collaboration that we find solution to complex problems and create new technologies that have positive impact on society. And indeed, as Professor Chowdhury just mentioned earlier about the knowledge gap, actually working on vacuum on surface science would force stakeholders to limit this gap, or rather to help bridge this gap to a great extent. So because I see some young people here, and I can't help it being a teacher in part of my life and working on research, I thought, why not throw in a spanner in the work and ask you, when was the first, where is, or what is the first reference in history? What is the first reference for vacuum? Just a line of research, but just to contribute in it a little bit. I came across a debate which was between two faqih, two jurists, two Islamic jurists from the 11th centuries, around 1025, 1050 AD. They were discussing at the time whether air is a tangible material or not. So remember, in those times, air today, we know what it is. We use it, in fact, we overuse air, and even we abuse it, unfortunately. But at the time, the question was whether air existed or not, whether it has a mass or not. And one of them said, Ibn al-Hajib, if my memory serves me well, he said, it is actually a substance, it is a matter, because the evidence is, if you wave a stick rapidly, you hear an echo, and that echo is a result of a collision between the stick in your hand and the air around it. So it must exist. There is evidence. Then he said to him, the other one said, so So give it to me then, hold it to me, give me some air, hold it, give it to me in my hand. He said, you is around you, but if you remove it, you will get emptiness. And to me, that is vacuum. So this is a reference in, I mean, it could, there may be something earlier, I don't know, but I'm throwing it to you guys, youngster, to find if there is a reference to vacuum science even before that. But at least this is a question I am proud to leave you with. And with that, I wish you a successful training course and thank you very much.
Thank you so much, Excellency, for your remarks. Before we move to the exhibition and poster presentations, we have a few sheets to give to our guests here for the inaugural session. If I can request you to move downstairs. Photo average here? Sure.
I think it's better we have.
So first, I would request the Coordinator General to present the shields on behalf of comstech. And I would also like to invite Her Excellency Ambassador North Cyprus to receive shields.
This is
One for our guest of honor, Mr. Imtiaz Rasta. And one for Professor Grant, please. Dr. Javed would also like to present a few shields on behalf of PBS. So, Tariq Saab, come present. To our chief guest. And also, sir, to the guest of honor, Mr. Imtiaz, sir. Thank you. Thank you so much, sir, for the shield distribution. And I would like to thank our guests here for the inaugural session. I would invite you all to visit our exhibition and poster presentation followed by IP. Please, sir. It's in the foyer, so right outside the hall to your right. And we'll be back here at 11:30 for our technical session. So please be back here on time for 11:30. So please, sir.
Auzu billahi minesh-shaytanir-rajim. Bismillahir-rahmanir-rahim. Dear participants, Assalamu alaikum and good morning. Now it's time to formally start the technical session. My name is Muhammad Arif, and on behalf of the organizing committee of this course, I welcome you all to this 3-day international technical training course on vacuum applications in applied surface sciences, jointly organized by Pakistan Vacuum Society and comstech. Ladies and gentlemen, the history of surface science actually starts with the history of science. Even in the Stone Age, natural pigments were used for the cave and the body paintings. Development of first deposition technique was started back in 1850s by Faraday, Grove, and Edison, and commercial introduction of electrochemistry was introduced by gold plating of uniform accessories. Today, with the development of science and technology, we can deposit materials down to atomic layer scale, and we can perform surface analysis by using electron probes. During this 3-day course, different surface analysis techniques will be discussed in detail. We will explore actually a very complex dimension of the material, that is the surface science. Ladies and gentlemen, vacuum environment is basically a prerequisite for many surface analysis techniques. We will start our session actually with the fundamental concepts of vacuum science and technology. So before this, I would like to introduce our first speaker, Professor Dr. Walayat Hussain. He will currently brief the outlines of this technical session, and after that, we will start the surface analysis techniques. Professor Dr. Walayat Hussain is currently serving as the Department of Material Science and Engineering at IST Islamabad. He did his PhD from USA, and his area of specialization is allied development. May I invite Dr. Walayat Hussain to come to the stage and introduce the technical aspects of this course. Sir, please.
Bismillahirrahmanirrahim. Assalamu alaikum. Thank you, Dr. Arif. We begin the technical session, and this is the introduction about this course. So we are here for 3 days, and we'll be talking about vacuum surfaces. And this is the 29th course from IVST platform, jointly organized by Pakistan Vacuum Society and comstech. And we have the collaboration from Pakistan Science Foundation and NINVAS, National Institute of Vacuum Science and Technology. Our main speaker, Dr. John Grant, has already told you about IVST. Just few sentences. This is an excellent forum for people working in the field of vacuum and its application in material science. The forum started in 1958 in Belgium, and now we have today's figure is 33. We have 33 member states, national vacuum societies, organizations working together in collaboration. And that means more than 15,000 people interacting with each other, collaborating and exchanging the information about this important field. It is good that IVSTA helps in organizing courses in various countries so that people from those countries can get knowledge about this important field. So our key person is Professor Dr. John Grant from the United States. He is the expert. He's expert. He has the experience of more than 40 years in this field, has remained distinguished research scientist at the University of Dayton. And of course, he has so many publications and one important book, which becomes reference in this field on the surface analysis by Auger and XPS. And we would not like to keep Professor Grant busy for 3 days. It would be too much. So we have some other speakers also. And Dr. Arif will talk about vacuum coatings, in particular about the assessment of the sources, the sputtering sources, what happens to them. There may be poisoning. So he will be talking about various techniques and then the assessment of targets. We have Dr. Shahzad Alam. He'll be talking about something new, nano composite coatings prepared by special techniques. So he will be talking about what they are, how they are fabricated, and then characterize them, and then application of those things. Then we'll be having Dr. Asad. He'll be talking about various types of coating methods using vacuum. In particular, he will talk about use of vacuum in plasma spray technology. Combination of plasma and vacuum provides unique opportunities for getting special coatings. So in between all these, you have exhibition, you have products about the vacuum technology. You can see posters, you can discuss with experts, exchange information, and a social gathering. But why we are here? How we can connect the dots, vacuum, surface, material science, all these things, how can we relate all these things? We begin with the material science. You know, the technology development is limited by the availability of materials. So that is why material science is progressing so rapidly. We have to keep pace with the technology development. And what is material science? We basically talk about property, structure, and processing relationship. If you can understand this relationship, you become material scientist. Property is our requirement. What function we want to have from that particular material. And that property will be obtained if you have a certain kind of structure. How will you get that structure? That depends on the processing. So if you can understand this relationship, you become a material scientist. And whenever we talk about the application of materials, most important property is the surface. What kind of surface you have? So we'll be talking a lot about these surfaces in this course. And vacuum technology. It is important to create special forces, to create special surfaces, to maintain them, to apply them, and in particular to characterize them. What they are, how they will behave, are they proper for us or not? So all these things, there's a relation between surfaces and vacuum. And when we talk about surfaces, we know the corrosion, erosion, wear, all these properties depend on the surface. surface characteristics of materials. Fatigue. If you want to improve the fatigue life, you would like to improve the surface. But these are kind of old metallurgical things. Now what people are talking about are special requirements of the surfaces. We are talking about hydrophobic surfaces. We are talking about hydrophilic surfaces. We are talking about biocompatibility of materials. We are talking about thin films, optoelectronics. We are talking about thermal management, thermal barrier coatings. We are talking about special sensors using nanomaterials where surface is important. We are talking about catalyst, nano catalyst, various kind of catalyst, all surface phenomena. So surfaces are important. Then vacuum. What is vacuum? In one slide, if you want to know, this is the one. We want to remove the air or gases from our system. So either we are removing these things from our system or from the surrounding of the material we are using. And how we will do that? So we have to create vacuum. We have vacuum pumps to create and maintain vacuum. That is the first thing. But there are so many kinds of vacuum pumps depending on your requirement. That is another topic. Then you would like to know what is the level of the vacuum. And then it becomes the gauges. Gauges will actually measure the pressure. And if pressure is low, we call it vacuum. And if you have a system under vacuum, you would like to control it, you would want to isolate it from the surrounding. So you'll be needing seals and valves. So these things become vacuum system through which you will be working with. So vacuum technology has an important role in fabrication of these special surfaces. You will be needing vacuum for preparation of special surfaces as well as applications. But the critical part is the analysis. You have to characterize the surface, and for that, vacuum is essential. And what do we mean by characterizing the surface? Basically, we want to know the properties of the surface, physical, chemical, and mechanical properties. But how will we relate these properties to what we have prepared? So we would like to know the morphology, what particles are present, what is the microstructure, even fracture surfaces. Then we would like to know what phases are present, what is the shape, size, and distribution of various phases. But in particular, we'll be interested in the composition, macro composition, micro composition, or even nano composition, and composition at nano level, almost atomic levels. Their distribution is important, where various elements are located. Are they segregated? Are they uniformly distributed? In which phase they are there? We would like to know, because that will define the characteristic of the surface. And then the bonding. When you have different types of atoms on the surface, you would like to know the information about the bonding between those atoms. All these become the characterization. You have different techniques, different methods to evaluate all these things. So we start with see, when Dalton told that matter consists of small particles called atoms, people started thinking about seeing the atom. So if you look at the lead pencil, this is graphite. And if you see in the optical microscope, you'll see something like this. If you go to electron microscope like this, and the ultimate would come when you go to scanning tunneling microscope, you will see actually the positions of atoms on that particular plane. So this is the ultimate as far as the atomic structure is concerned. And I would like to stop here because Professor Grant would be giving his lecture in the beginning. we can continue this discussion after the lunch. So up to this point, if you have any comment, any remark, then we leave this stage for Professor Grant. Any comment? Don't ask difficult questions. So do you like the connection between these things? Importance of surfaces and the importance of characterizing them. And what does characterization mean? If you can connect the dots, my work is done. Thank you.
Thank you, sir, for your brief introduction of the course. So we have an announcement. Actually, as you already knows that tomorrow evening we are going to organize a cultural show. So we are circulating information. Please confirm your availability for this cultural show. Okay, the cultural show is basically along with the dinner. Thank you for correction. So once again, we are back to the technical session. We are honored to have the presence of Professor Dr. John T. Grant. Dr. Grant has extensive experience in the field of surface science, having worked in this area for over 35 years. He is an expert with the techniques used in such studies. He worked in this field in Australia, Europe, and United States, and he is an internationally recognized authority in the field of surface science. Ladies and gentlemen, surfaces are the most complex component of the materials. I would like to quote the statement of Nobel Prize winner Wolfgang Pauli: "God made solids, but surfaces were the work of devil." This emphasizes the diabolic nature of the surface. Professor Grant has extensive experience in the Ozzy-electron spectroscopy. This is a surface-sensitive analytical method that provides compositional information in the near surface environment. It is one of the most commonly used implied surface analysis technique. Dr. Grant has contributed many advances in Ozzy-electron spectroscopy and X-ray photoelectron spectroscopy. Dr. Grant is also a fellow of American Vacuum Society and a life member of Institute of Electrical and Electronics Engineers. It's my pleasure to invite Dr. John Grant for his talk. Sir, please.
Okay, well, I guess good afternoon now, everybody. And thank you for your kind welcome. And yes, I've been working in surface analysis for a long time. And I took my first Auger spectrum back in 1968, long time ago. And then XPS in the early 70s. So I've grown up with these techniques, and they're absolutely fantastic. Dr. Hussain mentioned the importance of the surfaces. So the surfaces, we interact with the environment through the surfaces. So it's extremely important to know that the surface is not the same as the bulk. A lot of people think that the surface is the same as the bulk, but it most likely is not. And also he mentioned about the composition is not uniform. It can change laterally. So you can have different areas of the surface with different compositions. And also the bonding. He mentioned also about the bonding. And in many cases, we can learn about the bonding. So besides determining what elements are present, we can often tell if it's a carbide or something like that, which is extremely important because in steels and things like that, you can have graphitic inclusions, you can have carbides, different things. So this is one of the early areas of analysis in using Auger spectroscopy in the steel industry. And today, Auger spectroscopy is used a lot in the semiconductor industry. We're looking at small areas and characterizing those materials. Also, the technique called X-ray photoelectron spectroscopy, also called ESCA, and I'll show you these slides later. Also important technique. And the early instruments, actually commercial instruments that came out, the first one I used was in the early 1970s. And it was actually made by Varian. And Varian was one of the best vacuum companies in the world. They developed the conflat flange, the Wheeler flange. And when they came to make their analysis machines, their XPS machine, surprisingly, when I went to use one of these machines to do an analysis on titanium, basically I was trying to do studies comparing titanium metal with different oxides, titanium monoxide, titanium dioxide. And you can distinguish these quite easily with the Auger spectroscopy. And I wanted to do a study with X-ray photoelectron spectroscopy. And in that instrument that I went to use, after these samples had been in air, for example, titanium metal is going to oxidize, the surface will be contaminated. So you need to use the technique of sputtering with inert gas ions to remove the surface contaminants to get pure titanium. Well, I was really shocked to find that in my analysis, I did not get pure titanium. I had titanium oxides. And the reason for that was because the vacuum was not high enough. The vacuum was not good. And here we had a manufacturer who knew how to make ultra-high vacuum systems, but decided not to use that technology in their surface analysis instruments. And I was shocked. And in talking to a colleague at Varian later, it turned out that was because of internal politics. The divisions involved with the instrumentation and also with vacuum technology, those people did not get on well together. And the person developing the instrument did not want to use the other division's good vacuum technology, which is absolutely unbelievable. So they built these instruments, sold them for lots of money. People thought they'd be great, and they went out of business in that area. Basically, there were no use to anybody really for doing analysis. And a lot of people that made these instruments didn't understand what they really analyzed. So education is extremely important. So in my courses, I like to educate people about these techniques to help you understand the principles of the techniques, how they work, what they are, what you can do with them, and what you can't do with them. So that if you have a need to characterize the surface composition of a material, you have a good idea what techniques are out there and which ones might be best for your analysis. And you may not have the instrument, but maybe a university or a company nearby or somewhere else can do the analysis for you. But also it's important to be able to interpret the data, because I've seen a lot of reports from commercial organizations that do analyses for customers, which are incorrect. And one of the problems with that is the lack of knowledge. They rely upon computers to do the data interpretation. And some manufacturers today even sell machines that they guarantee are automatic. You have a sample, you put it on a platen, it goes into the vacuum system automatically. All the X-ray source or whatever comes on automatically. It does an analysis, it makes up the result and prints out a report automatically. And that is not good because they often make mistakes. And if you get the wrong analysis, you're going to be on the wrong path to do your production development, whatever you're analyzing and so forth. And you don't want that to happen. So even though companies claim they have experts, it's always good to know how these techniques work so you can actually check them and make sure the results that you've got are indeed valid. So that's why it's extremely important to understand these techniques. And also in your careers, when you're doing analyses, it's important to have a big toolbox where you know about all these different techniques, so you can select one for your analysis. So during the course, I'm going to talk about some different analysis techniques, mainly electron spectroscopies. That's my main background in electron spectroscopies, but also ion spectroscopies, where you're using ion beams to do your analysis. And they have certain properties also that are very, very important, where you can do analyses you can't do with electron spectroscopy. And then also briefly at the end, talk about some other techniques using X-rays and microscopes. Dr. Sain showed you graphite going from the a pencil down to the scanning tunneling microscope, where you can image the atoms. And this is also extremely important to have a basic knowledge of these techniques. So again, you can select the correct ones for doing your analysis. I was actually at a conference. It was the early 80s, 82 or 83 in Belgium. It was also a Vista conference. That was a European conference on surface science. And that was the first time that Binnig and Rohrer talked about their scanning tunneling microscope. And I could not believe what they did. To me, the invention of a scanning tunneling microscope where you could image atoms was unbelievable. Before that, you could only really image them with a transmission electron microscope to some extent, or with the Erwin Muller had also a microscope where he pulled off atoms from a sharp tip. You could study the atoms where they were on a sharp tip and image those, and also pull them off and identify them. But to do it in a basically, and you could do it in air, you did not need vacuum to do it, was actually, to me, incredible. And they did mention one thing, and that was that they were not supposed to develop that STM. They worked at IBM, and after some time, IBM told them not to work on that project anymore. They felt that it was not going to lead to anything, and they were not allowed to continue working on it. Well, like perhaps many good scientists and engineers, what did they do? They thought that they could actually make it work. So they continued working on it without IBM's knowledge and ended up developing it. And once they developed it, and they also received Nobel Prize for developing the STM, IBM was so proud of them. Okay, complete change. So that happens in life. You have an idea, you have a belief, you have some feeling that you can do something, and some boss tells you you can't do it. You're wasting your time. Okay, well, maybe you have to do it on your own time. But if you have an idea, then you must continue that idea if you believe in it. And sometimes people will leave a company to make their own company to develop something. And that can be very difficult because of lack of financing and so forth. But you have a dream, you know, you need to continue that dream. So anyway, that's just a little aside about some things that that happened in these fields that I thought might be interesting to you. Okay, so here are is my opening slide. Now, do people have copies of my slides? Do they have copies? They do? Okay, because I was checking and some people told me they didn't have copies of the slides. Could you? You have prepared the slides? I don't think so, because I asked some people at the break and they didn't have them yet. Are they outside? You're going to check? Okay, because it's very important to have copies so you don't have to spend a lot of time trying to make notes on the slides. And of course, I'm going to talk about a lot of things and you can just add notes, your own notes to them. So it becomes like a little book for you. And it's impossible to write everything down that I talk about. And I talk more slowly than I used to talk. Australians talk very quickly. And even when I first went to America, they couldn't follow me. And because I would talk so quickly. And then we had other quirks, like I worked in electron diffraction early on, low energy electron diffraction, and we were looking at the surface structures of materials. And so you work in a dark room. So the first time I was doing that, I asked them for a torch and they were taken aback and they thought this primitive Australian wants a torch. Well, to Americans, a torch is one of those things you hold like the Olympic Games and it has a big flame on it, you know? So in America, it's a flashlight. So there was a lot of cultural things that we had to exchange. So anyway, that is interesting. So I've had a very enjoyable career and love my work, love interacting with other people, and I love teaching, and I love passing on my knowledge to next generations so they can get the best analysis possible in their research when they need analysis using surface techniques. And the pointed one, on screen. I don't, oh, there it is. There's the laser pointer. Does that work also? Does that work also? Pointer? Oh, yeah, excellent, thank you. Okay, well, while we work out about getting copies of the slides. Oh, okay. Are these the so just wait a few minutes when we pass out these copies. It'll make it so much easier for you to follow along on the course. Well, you can see you're basically getting a book. Okay. So I teach different kinds of courses. My course, for example, on X-ray photoelectron spectroscopy that I teach is a 3-day course. So it gets into a lot of details. We're not going to do just that technique over these 3 days. We're going to use different techniques. So I've prepared these specially for you. And also in the back, there are reprints from articles that also describe their techniques in more detail as well for you. Okay, well, let's start off about surface analysis. In surface analysis, we want to identify the elements that are present at the surface. And that's called a qualitative analysis. We need to know what the elements are on the surface. Sometimes we would like to know the concentrations of the elements as well. And that is not always easy to do, but that is called a quantitative analysis. And generally, a qualitative analysis might be all you need. For example, if you're making certain devices and something works and something does not work, by comparing one with the other, you might find a certain contaminant present that is causing the problem. And it's not necessary to know how much is there because that's the problem. So the quantitative analysis can be more difficult, particularly in Auger spectroscopy, to do a quantitative analysis. And as was mentioned, chemical bonding at the surface, the chemical bonding state is also greatly important. And that's the chemistry of the surface. And the distribution of the elements across the surface can be different. And that gives us basically an image or a map of an element across part of a surface. So these are all important things to learn about a material surface. And often you'll want to know what the composition is below the surface. So we can also do what's called a depth profile, which is a change in composition with depth from the original surface. So depth profiling is also extremely important to look at the near surface composition. You might be looking at thin films and you want to look at the interface of something like that. So extremely important. And as Dr. Hussain mentioned, the processes occurring at surfaces are also great importance. Many areas of research need surface analysis to really understand or to develop new materials. Catalysis, corrosion, polymers, semiconductors, coatings, adhesion, wear, lots of areas. We also mentioned about growing materials, atomic layer at a time, where you can make a material that does not exist in nature. For example, in what's called molecular beam epitaxy, where you can actually make a device with certain properties, maybe for optical sensing or something like that. So all these techniques, all these areas of materials development need surface analysis in the development of properties. And the surface has about 10 to the 15 atoms per square centimeter. That just gives you a general idea of how many atoms you're looking at in a certain area of the surface. It's a big number, but it's a small number compared to the number of atoms in the bulk of the material. Something like that. So depending upon your beam of analysis or your area of analysis, you can estimate how many atoms you might be looking at in a surface. The other thing is, if I take a bulk material and fracture it or break it, if I break it in air, if it's a reactive metal like tungsten or titanium, the molecules from the air are going to come and very quickly absorb on the surface and form, for example, oxide. And that's going to happen in a very short time. As a matter of fact, a nanosecond. It's a very reactive material. It's very quick reaction. So if you want to study clean metals, you have to work in ultra-high vacuum so that the metal stays clean. So it is possible to fracture samples in the vacuum system. So there are devices where you can actually fracture material in the ultra-high vacuum. So it stays basically clean after fracture. If you, and that's a very important area, is particularly in OJ spectroscopy, to study the fracture surfaces of materials. Another very important slide is this one that talks about the types of surfaces. Often people doing analysis think that the surface is ideal. It's the same composition laterally and with depth, but that's not generally the case. Because a sample you have is generally going to have a contaminant film on it. Say it's a sample from a bearing or something like that. You're interested in looking at the wear. It's going to have contamination on the surface. It'll have oils, something like that. So you have to be able to prepare the sample to remove some of these things from the surface. The surface techniques are so surface sensitive that even a fingerprint, if you put a fingerprint on the surface of material, you can not get any signal from that material. All you get is a signal from the fingerprint. I'll show you that later. Also, you might have a microstructure. You might be putting down a certain structure on purpose. You might be making a device, electronic device, and you're putting down the film in certain areas. Then it becomes a question of spatial resolution. What area can I measure? Can I measure the composition of these different places? Can I measure the composition on the surface of these films and separately in between? Because if my spatial resolution is not big enough, I'm going to get an average composition across this region here. So spatial resolution is also an important consideration. It's like in the scanning electron microscope. I volunteer for high school students to come in and use electron microscopes. And they come in and they actually can image different things. And one of the things I like to look at is a butterfly wing. And butterfly wings have lots of structure. And the students, when they first look at a butterfly wing, will say, wow, that's pretty nice. But I say, why don't you increase the magnification? Then they'll start to see a substructure when they do that. And they say, oh, wow, focus on that. And they think that's done. I say, increase the magnification again. And they go again and they find a new microstructure. So people sometimes don't look at the great details. They'll get just an average composition or something like that and miss the real beauty of nature and things like that. So the surface microstructure, the spatial resolution is also important. The region between a thin film and what we call a substrate is referred to as the interface. And that's also important because sometimes we want to build up diffusion barriers. We don't want something from a substrate diffusing up to the surface of the thin film. So often you might put down a special layer of a material to stop diffusion from the substrate into the thin film that you deposited. And that's where the depth profile comes in important. You can actually look at the composition with depth and get an idea of the composition of the film and the interface, and then the substrate. And down the bottom left there, mentioned about a sample being laterally homogeneous. This is an example of polycrystalline materials. So polycrystalline materials, this might be iron, but we have different areas of the polycrystals. And if we look at a particular place on this material, if we have high spatial resolution and look at this region, we'll see iron. If we look at this region, we'll see iron. But what happens is the intensity can vary. So the intensity you get in analysis can depend upon the crystal orientation. So if you're looking at polycrystalline materials or single crystals, the intensity of signals can vary depending upon the grain. orientation. And finally, most surfaces that we look at are rough. They have a certain degree of roughness. It might be macroscopic, where you can see it with the eye, or it might be microscopic, where it's actually on a more of atomic scale. So these are some factors to remember in doing a surface analysis measurement, that the surfaces is generally not ideal. Now, the techniques that I'm going to talk about over these 3 days, I'm going to start off with the first one, AES is the acronym, Auger electron spectroscopy. And AES is also used for atomic emission spectroscopy. So the same term is used for different techniques. But we're specifically talking about Auger electron spectroscopy. And it's named after the Frenchman, Pierre Auger, and that's why it's called Auger electron spectroscopy. And we're going to talk about X-ray photoelectron spectroscopy, XPS. It's also sometimes called ESCA, electron spectroscopy for chemical analysis. So these two basically are the same technique, just different names are sometimes used. But XPS is the preferred name. And then in ion spectroscopies, I'm going to talk about ion scattering spectroscopy, which is the most surface sensitive of all these spectroscopies, ion scattering spectroscopy. It has the capability of just looking at the top layer, not even the second layer of material, just the top layer. It's the most surface sensitive of all of these. And then secondary ion mass spectrometry, where we're looking at the ions coming off a surface after it's been impacted by an ion beam. So you have an ion beam coming in, and you're looking at the ions coming out of the material. That's secondary ion mass spectrometry. A variation of that is called sputtered neutral mass spectrometry. It turns out most of the particles coming off the surface when they're impacted by an ion beam are neutral particles, not ions. So in secondary ion mass spectrometry, we're looking at the ions coming off. And the ions could be positive ions or they could be negative ions that come off. And we can look at both of those separately. But again, most of the particles coming off are neutrals. So there is a technique that looks at those neutrals that come off, called the sputtered neutral mass spectrometry. Rutherford backscattering spectrometry is also very useful for looking at particularly thin films. And total reflection X-ray fluorescence is also a very important technique. Many of you might be using X-ray fluorescence, but this is a total reflection variation on X-ray fluorescence, so you can enhance the surface composition in the analysis. And finally, scanning probe microscopy, where we have the capability of looking at the actual individual atoms, things like that. So we're going to start off with electron spectroscopies, Auger electron spectroscopy. And in Auger spectroscopy, we use a focused, energetic electron beam as a probe. And when we use an electron beam as a probe, that electron beam can produce these Auger electrons. And I'm going to talk about how we produce them from the sample. Well, these Auger electrons are produced in the material, and some of them escape from the surface and get measured in a spectrometer. So we measure the kinetic energy of the electrons coming out, and the Auger electrons have unique kinetic energies when they come out. So we measure the peaks in the spectrum to identify the elements that are present at the surface. In XPS, X-ray photoelectron spectroscopy, we use soft X-rays as a probe. And the X-rays also produce electrons from the atoms in the material. And those electrons that come out, again, some of those will escape from the surface, and we measure them as well. And we measure those as a function of their kinetic energy. And again, identify the composition with that technique as well. So these two techniques are electron spectroscopies. One uses an incoming electron beam, One uses soft X-ray beam, and we're looking at the electron spectrum coming out of the material to analyze the surface composition. And here's just a diagram showing you the interaction of electron beam with the sample. Our primary beam comes in from our electron source, penetrates into the material, and the electrons scatter. And the high-energy electrons typically form this inverted balloon shape in the material. And in this volume here shown in purple, we can produce Auger electrons, because this is the region where we have energetic electrons. We can also produce X-rays. Like an electron microscope, we use EDS, looking at the characteristic X-rays coming out from the material, EDS. And we can also measure topography by looking at the secondary electrons or the backscattered electrons coming out of the material. And this balloon, this inverted balloon, typically has a depth of about 1 to 3 micrometers in the material, depending upon the energy of that beam coming in and also the material that we're looking at. But even though the Auger electrons are produced within this purple volume here, only those that can escape without losing energy will appear in the peak in the spectrum. And they can only come from near the surface. So the Auger electrons that come out are only coming from a very shallow depth in the material, about 0.4 to 5 nanometers in the material. So the signal that we get in our peaks in the spectrum is just from the surface, because the Auger electrons that come out that have been scattered from deeper in the material are going to lose energy and will not appear in the peak. I'll come back and mention that again later on. And this illustrates the Auger process. We have an incident electron here, and you can think of this as an atom. And in the atom, we have electrons in the different shells or different orbits. And I'm using X-ray notation. We use X-ray notation for Auger spectroscopy. We talk about the K shell, we talk about the L shells and so forth. And the K shell has 2 electrons. The L shell, it can be split into subshells we call L1, L2, and L3, and so forth. Well, the incident electron comes in, and the typical beam energy that we use in Auger electron spectroscopy, 3, 5, or 10, and even 25,000 electron volts. So we use a beam energy somewhere in that range. I typically use 5 or 10 in doing my Auger analysis. It depends on the instrument. Some instruments do not allow you to go to higher energies like 25 keV, but 3, 5, and 10 are commonly used, and mostly 5 or 10. So we have an electron beam coming in, let's say 10 keV energy. So those electrons have enough energy to remove an electron from one of these shells. So if the binding energy of an electron in one of these shells is less than the beam energy, there's a certain probability that that electron can be ejected from that shell. Of course, if the binding energy is bigger than my electron beam energy, I cannot eject it. So if I'm using a low beam energy like 3 keV, I cannot eject an electron from a shell that has a binding energy greater than 3 keV. And that's the binding energy is the energy that you have to give an electron to remove from the shell. That's how strongly it's bound to the atom. So the binding energy is the energy you have to give that electron just to get it free of that particular shell in a material. So binding energy is a very important term. We all also use the term electron volts, and the electron volt is a unit of energy, and it's the energy an electron attains in traveling through a potential difference of 1 volt. So electron traveling through a distance of 1 volt from 0 to 1 volt, just before it hits the 1 volt, plate, if we have two parallel plates, it'll gain an energy of 1 electron volt. So that's a unit of energy we use all the time in surface analysis techniques, is the electron volt. So after we create a vacancy, in this example, in the K shell, an electron's ejected from the K shell, one of the other electrons can drop down and fill that vacancy because the electrons want to be closest to the nucleus. They want to occupy these innermost shells. So electron's going to drop down from one of the other shells. In this case, I'm dropping electron down from an L2 shell to fill that vacancy. So now it's filled in, it's black. And when that electron drops down to fill that vacancy, it releases energy. And the energy released is just the difference in the binding energies. So the binding energy of the electron here is less than what it is here. So it has to release that energy in when it drops down to fill this vacancy. And that energy released can be released as an X-ray. And that's the technique, like the EDS, like electron microscope. Or the energy could be used to remove another electron from the atom. And then if that electron comes out of the atom, that's called the Auger electron. So Auger electrons involve 3 shells. An initial shell where we make a vacancy, electron dropping down to fill that vacancy, and then electron being ejected from the atom. So we use those 3 shells that are involved to label the Auger electron. So in this example, we call it K, L2, L3 Auger electron. That would be what we have here to label our Auger electron. K, L2, L3, because we have a K shell, L2 and L3 Auger electron involved. And the Auger electron kinetic energy is approximately the difference in those binding energies of the initial vacancy and the electron that drops down to fill the vacancy. That's shown here in the brackets. That's the energy that could also be released maybe as an X-ray. And then you must subtract off the binding energy of the other electron to see how much you have left over. And that will be the kinetic energy of that Auger electron coming out of the material. So by measuring the kinetic energies of electrons coming out of the material, we can tell what the atoms are. Because every atom is going to have a unique set of energies for the Auger electron, because each atom has a unique set of binding energies. And we don't detect hydrogen or helium directly with this technique because they don't have enough electrons. You need 3 electrons to see an Auger electron. So lithium is the lightest element that we can detect directly with Auger electron spectroscopy. And as I mentioned, the alternative in C is that an X-ray is emitted, and that's energy dispersive spectroscopy, for example. And instead of the electron being ejected, the X-ray is emitted. So we have these 2 competing processes. Sometimes an Auger electron is emitted, sometimes an X-ray is emitted, one or the other in our process. And this shows you the probability of the ejection of an Auger electron versus X-ray emission from a K-shell electron. So a K-shell electron, for the light elements, this is the atomic number down the bottom. I've labeled a few here: calcium, zinc, zirconium, and tin. You can see for light elements, the probability of an X-ray emission is extremely small. And that's why it's more difficult to detect light elements in X-ray emission, like EDS, than it is for heavier elements, because they come out as Auger electrons instead of X-rays. And you can see the probability of an Auger electron is almost 100%, 1.0 is a yield. But then as you go to heavier elements, they change. The probability for an Auger electron starts dropping off, and the probability for X-ray emission increases. And this is EDS, and this is Auger spectroscopy. So it turns out, though, in Auger spectroscopy, these are for the K shells. So you're typically going to have a KLL type transition. And when you go to heavier elements, you're going to have a different type transition. It's going to involve the L shell instead of the K shell. It'll be an LMM Auger transition instead. So you still have a high probability of having Auger emission for the other heavier elements because you're using different shells. You're not using the K shell anymore. And here's a picture of Pierre. It's named after him. He observed this back in the 1920s. And as I mentioned, we labeled them with the shells involved, if we know them. KL2, L3 is the example I showed you. You can also have different combinations of KL1, KL2, 3. When we put a comma in, it means that we don't know if it's an L2 or L3, because in that case, those binding energies are too close together. Or we can use a generic label like a KLL transition without specifying specifically which one it is. It's just a K, and L drops down to fill the vacancy, and L comes out. So we have KLL, Auger electrons. Or we have LMM or MNM. And sometimes we'll use the letter V, and V indicates a valence electron. Or sometimes you might see people use a C, and C denotes a core electron, one that is not involved in the bonding, one that stays with the core of the atom. So sometimes you might see this in literature. And Pierre Auger was a famous person, actually. He, besides basically given the name for Auger electron spectroscopy, discovering that effect, he also was an artist as well. And there's also a big project in South America called the Pierre project for looking at cosmic rays as well, named after him. So he had a lot of interests as well, besides Auger spectroscopy. And just as an aside, there's also a lady, Lisa Meitner. You might have heard of Lisa Meitner. She also observed Auger electron spectroscopy about the same time. So there was been a big argument about whether the technique should have been called Meitner spectroscopy rather than Auger spectroscopy. And there's been books written on this, actually, articles, publications, and so forth about this. And the community still feels that Pierre Auger was the first person to discover this process. And Lisa Meitner was also very involved in fission. She was very involved in that. And she was never really recognized. And but she does have an element named after her. One of the elements in the periodic table is named after Lisa Meitner, Meitnerium. There's a big periodic table I saw in the building, and you come in, if you look up there, you'll see an element named after her. So she had some recognition, but some people felt that she should also deserve recognition for this process. So here are spectra. This is the kind of thing that we see in taking a spectrum. We have two kinds of Auger spectra. Up the top, we have one that's called the direct spectrum. This is just terminology that the community has established and selected, direct spectrum. And you can see that the little bumps on top of the background are quite small. And these are the Auger electrons. So these little bumps here are the Auger electrons that come out of the material. And they're superimposed on a big background of secondary and backscattered electrons. So these are the Auger electrons. So there's a small percentage of the electrons coming out at any given kinetic energy are Auger electrons. So what we do is typically take a derivative today in the computer of a spectrum like this to enhance these Auger features. So this is called a derivative spectrum. And now you can see these features much more clearly because the background approximates a straight line. And when you take a derivative, you'll get a fixed number, and you can subtract that and make it 0 and amplify the signal. If you amplify this signal, the background just gets bigger and bigger, and the peaks don't get any easier to detect. So taking a derivative is typically what people use, and then you measure the intensities by these peak-to-peak heights of these features in the spectrum to do a quantitative analysis. So these are the two kinds that you get. In modern instruments, this is what you acquire. The spectrum is like this. And then in the computer, you will take the derivative to do your analysis. That's very typical. The only time you don't do that is when you're mapping. If you're taking an Auger map to see where the elements are at the surface, you'll still use the direct spectrum. And you'll measure the peak above the background is what you will typically use in doing a map. Okay. And here's a chart of the main or principal Auger electron energies. And on the horizontal axis, you can see the kinetic energies of the Auger electrons coming out here. This is the kinetic energies of the Auger electrons here. Here's the atomic number. And here are the elements, their symbols on here. So you can see we don't have hydrogen and helium. The first one's lithium. And they only basically have K and L electrons. So the Auger electrons are KLL Auger electrons, and that's the generic label put on here is KLL. And you can see as you go to heavier elements, the kinetic energies increase. But when you get up here to around 3000 EV, kinetic energy, you'll notice that you can also detect lower kinetic energy Auger electrons from the same element. And these will be the LMM Auger electrons. And then also, as you get to even heavier elements, you get the MNN Auger electrons. So we can always detect the element, except for hydrogen and helium, below, say, an energy of 2000 electron volts. We can always see a signal from each element below 2000. You might like to look at higher energies to confirm the presence of a certain element because some of the peaks overlap. But when the peaks overlap, you can have issues with peak identification, particularly for light elements, since they only have basically one Auger electron coming out and might interfere with a different element. So peak overlap problems can be an issue, but there are ways to get around that by spectrum subtraction and various chemometric methods in doing analysis. So this chart is very useful for identifying what the peaks are in a spectrum. And you can see that the LMMs, they separate out into 3 bands as we go to a higher atomic number. So you're expecting to see these triplet type peaks for those heavier elements and so forth. And for heavier elements like tungsten and so forth, we have lots of different peaks in a spectrum. So if I have an alloy, a metal alloy, so I have an alloy that has iron and chromium, for example, or maybe copper, you're going to have overlap issues because the peaks will overlap. So Auger electron spectroscopy can be difficult to interpret, but you can also take reference spectra and simulate the spectrum you might observe to get the composition, rather than just use spectrum subtraction techniques. So this chart is very useful. Also, handbooks of spectra. The handbooks of spectra show you a spectrum, the derivative spectrum. Here on the left, this is the handbook of Auger electron spectroscopy, put out by one of the manufacturers, Physical Electronics. It's now owned by a Japanese company. And the 3rd edition. So on one page, we have the derivative spectrum over a wide energy range, and this is copper. And over here on the other page, we see the direct spectra of different regions in the Auger spectrum, both in the direct and in the derivative as well here. So this is just an expansion of these peaks here. And this is an expansion of the peaks down there. And as I said, this is probably the most useful handbook for Auger spectroscopy. And it's important to really have a handbook because you can look up the handbook and see where the peak should be to confirm the composition. You just don't want to rely upon the computer because the computer will make mistakes. Also, you can look for overlap issues, different alloys, and have an idea beforehand what kind of issues might arise in your analysis. Some suggested books. The one at the top here, mentioned earlier, the book that Dave Briggs and I put out 20 years ago, Surface Analysis by Auger and X-ray photoelectron spectroscopy, 900 pages, has a lot of articles in there, things I'm not going to cover. For example, you can produce Auger electrons using positrons. Okay, has certain properties. You can also produce in some materials, you can also produce Auger electrons from an ion beam, only in certain materials. So lots of different things are covered in this book that I don't have time to talk about here. We're just talking about the electron beam excitation. And then other books here also listed. One by John Watts and John Wolstenholme. Surface Analysis, the Principal Techniques also includes information about the ion techniques. And second edition. And this is really an excellent book. So the number 3 book here on the list, this is one that's more affordable. And I recommend this one if you have a limited budget. As a matter of fact, I just asked Ian Gilmore recently about helping him with the project, and he said, no, he didn't have time because he's working on the 3rd edition of this book. Okay, so this is an excellent book here because it covers many different techniques in surface analysis. This book is specifically on scanning Auger electron microscopy. Martin Prutton is the world authority in scanning microscopy. He built his own machine to do scanning microscopy before the manufacturers really built good machines. And University of York in the UK. And in another book here by John Wolstenholme on Auger electron spectroscopy. And this one here is basically an ebook. It's printed on demand. Some publishers now don't print the books. They basically want to sell you an ebook, or if you want a hard copy, they make a hard copy for you. And I like to get copies of all the books. I like to read them and check them out. And when I got this book from John Wolstenholme's publisher, the Meta Press, I asked them if I could get a copy for free because I teach courses and I like to mention some of the books. So they said, oh, okay, we'll give you a book. So I got the book and read it. And lo and behold, there were quite a few errors in it regarding the history of the technique. And John Wolstenholme is one of the experts. He grew up with it too. And so after a couple of weeks, the publisher emailed me and said, well, what did you think of the book? I said, oh, it's a pretty good book, not too many errors. And of course, what the publisher's going to say, well, would you mind telling us what the errors are? And I thought, okay, I'll tell them what they are. And when I told them and John saw them, he sent me an email and said, John, I thank you for all these corrections. I just completely forgot about this or that. So, and that's nice when you have an ebook because they can modify it immediately before they print a copy for you. So they could print a copy and make those corrections. So even, I don't want to say everything in my book maybe is absolute, but when you read a book, be very careful because sometimes people do make errors. Nobody is really perfect, okay? Including me, I guess, too. Even though I like to have everything accurate. So when I edited this book, I read every chapter. I went through every chapter, hard and hard. And the publisher didn't like that because the publisher didn't want all these iterations of the chapters. They were quite happy with what it was, but I really wanted to read each one. And they refused to give me the final version of each chapter. They just proofread it and check it again. So that's some issue you can have too with publishers. The publishers got deadlines, they want to do something, they want to get their return on the investment. So these are good books, and libraries may have them. And as I mentioned, the book here, number 3, is a really good book because it covers many, many techniques. This illustrates how the electron trajectories can vary in different materials. Using a 10,000 electron volt beam on gold and silicon. And you can see here, this is what's called a Monte Carlo simulation. So you do a calculation with physics. You have electron coming in, and then you use physics to calculate out the scattering. And you do this on thousands of times, and you get an overall idea of where the scattering will be. So each one of these is an individual calculation, and this is the sum of thousands of calculations. And you can see in the case of gold, even though the beam might be very narrow and only strike a region on the surface here that's quite small, the electrons scatter. And this is like the inverted balloon that I showed you earlier. And this inverted balloon can produce the Auger electrons. And you see here that even though the beam strikes this point, the energetic electrons can also come out very close to the surface here. So Auger electrons can be produced outside the beam. So this is the beam, and Auger electrons are produced in this volume, but also produced right here near the surface. So you get a signal from the region surrounding where the beam's hitting. So the beam is hitting a certain point that you identify in a scanning mode, like a scanning electron microscope. But the Auger electrons aren't coming just from that point. A lot of people make that error. They think it's coming just from that point. But the energetic electrons can excite Auger electrons from nearby because of scattering. And in silicon, you can see the interaction is quite different. It's more of a pencil shape going into the material. You can still get some scattering back towards the surface, but most of them now are scattering inside the material. So these are called Monte Carlo simulations. And you can also make these yourself. There's a program put out by David Joy where you can do these simulations. You can change the angle of incidence of the beam. You can change the beam energy. He's also got some elements built in here. And you can simulate the scattering in the material here with a length marker. So this is something that can be useful if you want to get an idea of the distribution of electrons in the different materials, and it's free. He doesn't charge you for this particular simulation program. One of the problems that we have in Auger spectroscopy is this backscattering. So in the previous slides, like this one, when the electrons come in and scatter, this is forward scattering. But when the electrons come back towards the surface, this is called backscattering. So energetic electrons can be backscattered towards the surface. And these backscattered electrons also can produce Auger electrons. Well, if they backscatter towards the surface, they got a second chance to produce the Auger electrons and give us a signal. And that affects the quantitative analysis. So if you have a lot of backscattering, you can have a much bigger signal. So that's one of the issues in quantitative analysis and Auger spectroscopy. And unfortunately, the manufacturers do not include that in their software for doing quantitative analysis. So you can have quite large errors in quantitative analysis and Auger spectroscopy because they ignore backscattering in their software for doing the calculations. And this just shows you this 1 plus R. So this is the total backscattering, and the R is the increase. So if no backscattering occurred, R would be 0. So R represents how much extra signal you get because of backscattering. And you can see the signal can get doubled by backscattering. So the signal can be twice as big as what you would expect when you have significant backscattering, because those backscattering electrons can also excite Auger electrons near the surface when they come back towards the surface. So it depends upon the element. This is the atomic number. It also depends upon the binding energy of the shell that you're trying to produce an Auger electron from. The higher the binding energy of the shell, the smaller the backscattering, which is sort of logical, harder to produce the Auger electron. So this is called backscattering, and it's a correction factor for quantitative analysis. As I said, it's basically ignored by the manufacturers. So here's a measured spectrum that I took. And this is a complete spectrum. I'm using a very low beam energy here so you can see what the electron distribution is. So this is a 1000 electron volt beam. And if I measure the spectrum coming off the surface, the electrons coming out of the material, you can see I get quite a lot coming back at the same energy as my beam. So these are scattered elastically from the surface. They come back without losing energy. So this is called the backscattered primary electrons coming back at the same energy as my incident beam. And then as you go down to lower kinetic energies, you'll see structure here. This depends upon how the electrons lose energy in the material. And you'll see this broad background of backscattered electrons. And down here, secondary electrons. And if I amplify this region here up by 5 times, you can see the little bumps. There's a bump here. This corresponds to silicon. This bump corresponds to carbon, and this bump to oxygen. Again, that's why you take a derivative to be able to see these features more clearly, because in the direct spectrum, these features are hard to see. But this is a complete spectrum, and you can see the backscattered electrons have a much higher intensity than the Auger electrons. We'll finish at 1:30. No? No, okay. Okay. Well, I'm going to stop here. And when we come back, we'll continue talking about some of these polycrystalline effects, where if you have grains in a material, the intensities can vary depending upon the angle. Okay. So I hope you are learning something. Even though you're not using the technique, I think it's useful to understand the technique and what you can do. I'm going to show you examples because I got 2 more sessions this afternoon, and then continue on. So we're going to take our break now for lunch and prayers.
Thank you very much, sir. That's a nice start. So we have a 1 hour break, lunch break. We'll be back like 2:15. Thank you very much. So once again, welcome to the technical session of training course on vacuum application and applied software sciences. So I'd like to repeat another announcement. As already mentioned, that tomorrow we have arranged a dinner along with the cultural show. If you have not yet confirmed your participation, please inform the registration desk before leaving. And secondly, in the lecture notebook, we have provided a survey form. Kindly fill the form and return the same to the registration desk. Thank you. So let's again start the second session. In the first session, we gained a very good knowledge of the electron microscopy. As mentioned by Dr. Grant, vacuum environment is essential requirement for clean surfaces and their studies. So we will start again with the importance of vacuum science and technology. For this, I will invite Professor Dr. Walid Hussain for his talk on need of vacuum in science and engineering. Sir, please.
Welcome back after lunch. I will try my best that you may not sleep. So when we want to see the surface, we start with optical microscope, go to scanning electron, and if we are lucky, we could get to scanning tunneling microscope. We usually underrate optical microscope. It can do many things, but we can get beautiful micrographs. A lot of information is there. But the problem occurs as far as three aspects are concerned. The first is depth of field. You require highly polished surface to see in the optical microscope. So if you have a fracture surface of you, or if you want to see at a different level within a surface, you cannot use optical microscope. Then second problem is resolution. You cannot resolve things which are very close to each other. And the third is chemical information. You don't get chemical information from the optical microscope. So we have to go to electron microscope. And you will notice the connection why I am talking about these things. You'll be learning basic principles about the vacuum, use of vacuum in the analysis. This is the first thing about the depth of field. In a scanning electron microscope, you can see here, you effectively get a three-dimensional effect. The whole thing is in focus. In optical microscope only, a particular part would be in focus. So if you have something like that of fracture surface, you have to go to scanning electron microscope. Second thing is resolution. See, I asked my student what is the limit of magnification in optical microscope, and I get different answers. You can always have dozens of lenses and get magnification up to 100,000, but then you will not see anything. And the reason is the resolution. If you cannot distinguish two features very close to each other, then you have poor resolution. And the resolution depends on the wavelength of the radiation you are using for observation. When we use optical microscope, we are using visible radiation, and the range of wavelength is 400 to 700 nanometers. So the resolution comes out to be around 300 nanometers. If you have any feature less than this size, you will not be able to distinguish it. But we want to go to 1 nanometer, 2 nanometers, something like that. So we have to change the radiation. Actually, we have to decrease the wavelength. And if you want to decrease the wavelength, that is the reason why we go to electron beam or X-rays. So going back, when physics told us that every moving particle will have wave associated with it, so people said, oh, electron beam can have wavelength. And immediately, people thought about transmission electron microscope, use electron beam as radiation. And we got transmission electron microscope. And as we increase the accelerating voltage, we decrease the wavelength and we increase the resolution. For example, in transmission electron microscope, we have accelerating voltage from 40 to 1200 kilovolts, and the resolution can go up to 0.1 nanometer. That's almost 1 angstrom. And in scanning electron microscopes, we have smaller accelerating voltages, 1 to 30 kilovolts, and then the resolution is in the range of few nanometers. But that is good enough. That is much better than optical. So this is your transmission electron microscope, a very dedicated piece of equipment. It is delicate and you have to know how to operate it. You need a special technician. And the main problem is that we are using high vacuum. In fact, we have various chambers having different vacuum levels. And just imagine, you have a very small sample, specially prepared. It will have a small thin area, which is transparent to electrons. And you have to put that sample inside the microscope when it is under vacuum. So there are so many tricks involved, and you have to be careful. You don't disturb the vacuum, and you put your sample, observe, and take it out, and your system continues to work. It is a delicate piece of equipment. But you get a lot of information. You can get photographs, good micrographs, and there's so many things you can do. You get the bright field, just you photograph. And then you go to dark field. And instead of using the main beam, you just use the diffracted beam for the imaging. And you can illuminate that particular phase in which you are interested in. Then electron diffraction for the analysis of different phases. What is the arrangement of atoms? What is the structure within a particular phase? Then orientation relation. If you have two phases, what is the orientation relation between those two phases? And if you are lucky and if you have enough money, you could have a microscope for lattice imaging, high resolution electron microscope. And if you have more money, then you could attach a scanning coil within the transmission electron microscope, and then it is called scanning transmission electron microscope for chemical analysis of nanoparticles, very, very small particles, very, very thin films. So here we have a bright field image, dark field image, electron diffraction, and then electron diffraction from two phases, where you can get the orientation relation between two phases, alpha and gamma here. So a lot of information, but you need to know what you're doing and how to interpret these results. Lattice imaging, and ultimately the arrangement of atoms at various surfaces. So that is delicate. Now talk about a workhorse. An electron microscope, which is essential for any material science laboratory, that is a scanning electron microscope. And we have the advantage that sample preparation is not that difficult as compared to transmission. We can have big samples, failure samples for analysis. So it is fun. You get a lot of information easily, very nicely. You can get chemistry. You can do in situ experiments, all in vacuum. We have beautiful photographs. You feel the effect of third dimension, 3D effect. Very good depth of field. And this is, as Professor Grant told you, when there's interaction of the electron beam with your sample, there's so many things happening. You will have Auger electrons from the surface area, and then you will have secondary electrons from the top area, which we use for imaging of the surface. And then we have backscattered electrons, which will give you image, but that will be based on the elemental contrast. But the most important thing rather most alarming thing is the region from which you are getting characteristic X-rays. This we use for chemical analysis. And this figure you should remember whenever you are doing analysis of the small particles. Remember, as Professor Grant told, this volume is about 1 to 3 micrometer. So you are looking at a nanometer particle, but you are getting chemical information from 1 to 3 micrometer region. And that could be deceiving. So you have to be careful about that. This is an important slide, I think. So this is the chemical information you get. You can, your computer will do the calculations to give you quantitative analysis. But you have to remember few things. This is for the students. Please note these things. Sometimes we get problem of the overlap of two peaks. I remember I gave a sample in which I was expecting 5% molybdenum. And the operator told me you have 5% sulfur. And you know, sulfur is a bad element in ferrous metals. And if somebody tells you you have 5% sulfur, so that is a killer for you. So I went to him and I checked, there was a problem of overlap of peaks. So you have to, as Professor Grant told, you cannot rely on the operator. You should be there. You should know what you are doing, and you should be able to analyze the results in respect of your problem. Then we cannot rely on the signals from carbon, oxygen, and halogen. They are coming from your fingerprints. They are coming from atmosphere. They are coming from environment. So if you say SEM is telling me 12% carbon in my stainless steel sample, that would be horrible. But stainless steel is not supposed to have carbon, and you are saying 12% carbon. That would be terrible. But the level of vacuum we have in SEM will give you these things. Oh, these vacuums, think about number of atoms. Even if we have very good vacuum, there is a large number of atoms striking the surface and sticking on the surface, giving you wrong results. And then when you are analyzing thin films or small particles, remember that large volume. You are getting information from a large volume. So these things are for the students when they are doing research. They should remember these things. This is the elemental distribution. You can check any element of your interest, how it is distributed on the surface. And nowadays you can do a lot of experiments within the scanning electron microscope. You can have hot stage where you can carry out reactions, creep test. You can do tensile test, impact test within the microscope and look at the fresh fracture surfaces. Now, why we require vacuum in electron microscope? There's so many reasons, but 4 reasons are very important. First is the electron scattering. When you have an electron beam, you would like to have very narrow range of the wavelength. But if there are air molecules or gas molecules striking, electron beam striking with those molecules, their energy will change. That will change the wavelength. That will give you a large range of wavelength. And then you cannot get good images or good results. Second thing is when you have air or gas molecules and electron beam strike, you may have ionization. So electrical discharges. That would be the end of the world. Qiyamah hogi. So we don't want to have that. And then filaments are very important. Their life. If in particular we have higher vacuum in filament area, if you don't have high vacuum, they will burn out and their life will be very. Some filaments are very, very tricky in this respect. We'll talk about that. And finally, if you have any gas or air in your chamber and electron beam is striking, then you will be depositing those gas or air molecules on the surface of your sample. contaminating it and giving you wrong information. So these are basic 4 things why you require vacuum, not only in electron microscope, but in all these kinds of equipment where you are using electron beam as your primary beam and you are getting information from the secondary radiation. And what about vacuum we are talking about? Basically, see, when you want to have high vacuum, you need a series of vacuum pumps. So we start with the atmosphere, we go to low vacuum using a roughing pump. Then we go to medium vacuum using a diffusion pump or a turbomolecular pump. Then we go to higher vacuum using ion pump. And in many microscopes, we have cryogenic pumping near your sample. If you have a cold finger, so your sample will not have contamination because those contaminants will get frozen by that cold finger. That cold finger will be having liquid nitrogen with a temperature of minus 196. And since most of the roughing pumps and diffusion pumps employ oil, that we don't like. If there is back streaming, that would be dangerous. So modern trend is to use dry rotary pump and then go to turbomolecular pump and then go to ion pump. So we avoid ordinary rotary pump and we avoid diffusion pump. This is nowadays the standard. For the electron source, you will have different kind of filaments. Most popular is the cheapest would be tungsten filament thermal. You just heat it and electrons are released. That is cheap. Then we go to lanthanum hexaboride, Schottky emitter. And finally, we go to cold field emission. This is very interesting. If you follow this line, you'll see that tungsten filament has a very high temperature. And temperature is decreasing until you get cold field emission, almost room temperature. But that is not important. The important thing is you are increasing the brightness to much higher level. Even that is not very important. The most important thing is the range of wavelengths you are getting. And if you have a large range of electron wavelength, your resolution will not be good. Just like in optical cameras and optical microscope, you get chromatic aberration. You'll get similar thing in your electron microscope. So these field emission guns, you might have heard FEG, field emission gun, SEM. They are expensive, but then you get very good resolution, and you can easily look at the nanoparticles. So for observation nanoparticles, we go to field FEG, SEM, field emission gun, SEM. But they are expensive. Field emission gun. In my university last year, it cost about 40 lakh rupees to change that filament. And you have to change it within 2 years. So things are expensive, but if you have to look at the nanometers, nanoparticles, you have to afford it. And for that kind of filament, field emission, you will require very high vacuum. You have to be very careful to maintain that vacuum. So this becomes delicate. So we have different chambers having different levels of vacuum, and they are separated by small apertures. And some things for the operators and the students to remember, that we have to avoid volatile things. We want to avoid contamination of the chamber. In particular, one very strange thing. You have high vacuum and you want to open your microscope. So you will have to introduce something like air. But if you introduce air, you get moisture. So you have to use inert gas. We use nitrogen. But then you have to be careful about nitrogen itself. It should be dry. we have to be very careful, use dry nitrogen for opening the chamber. You introduce dry nitrogen and then open the chamber. Otherwise, very quickly you get your chamber contaminated. But sometimes when biological people come, we cannot use high vacuum. So we go to some other arrangement known as environmental SEM. There we have lower vacuum, but if you have lower vacuum, then you require a different detector. Low vacuum secondary electron detector. So again, this is a special thing, but necessary for biological samples. Something to add, very interesting. I like it, very fascinating. You combine your field emission gun electron microscope with focused ion beam and gas injection system. And then you can get so many things. You can do so many things on nano level. This is some other world. So using focused ion beam, I'll be doing milling on a nano scale. I'll be doing ion implementation. I'll be doing ion deposition. And when I combine focused ion beam with gas injection system, I can do enhanced etching. People are doing, they have a special interest, they do these things. Enhanced etching, selective etching, and material deposition. They are doing, they call it manipulation at nano level. But the thing which astonished me was the mass spectrometer at such a level, where you can analyze a nanoparticle and find what isotopes are there within that. That's something strange. At such a small scale, you can distinguish between various isotopes. Again, as Professor Grant told, that some of the techniques do not require vacuum. In principle, in theory, they do not require vacuum, but if you want to get good results, if you want to get high resolution, you would like to employ vacuum rather than doing that experiment in air. And when you are analyzing, the important thing becomes monolayer time. I will not go into theory, Professor Grant will be talking about that, but simple thing, if you remember. Okay, if you have a fresh surface in in your vacuum chamber, very quickly it will get atoms from the chamber, and that is, we are interested in this monolayer formation time. We want to have this time long so that we can analyze our sample before we get a monolayer formed on our surface, and that will depend on the vacuum level. If you have a very high vacuum, the monolayer formation time would be very high. You can easily analyze your sample before your sample gets contaminated. And as you'll be talking in detail, your primary beam could be photon, electron, or ion. And the information you are getting from your sample, that may also consist of photon, electron, and ion. And combination of these 6 things, you get all types of surface analysis techniques. I will not go into detail, but this is a very simple slide telling you all kinds of various surface analysis techniques. Few experiences just to keep you awake. When I went for PhD in 1979, University of Connecticut, and at that time only few universities had that Auger electron microscopy. As Professor Grant told, it started in 1968, and by 1979, not all the universities had Auger electron spectroscopy. And my professor told me that that was a time when shape memory alloys were coming into market, and the first alloy was nickel titanium. But then people realized that alloy is very good, you can do a lot of work, but it is expensive. So people started working on shape memory alloys which are cheaper. And this was one, copper, aluminum, nickel. But when my professor started working on this, he was working in Kennecott Copper Corporation before coming to university. He found that they are extremely brittle and they break through grain boundary. So he asked me, okay, go analyze, find what is the reason, what impurities are there, and try to find ways to overcome this. And at that time, it was very clear that temper embrittlement in steel is due to segregation of impurities at grain boundary. And these are the culprit elements: antimony, bismuth, arsenic, tin, phosphorus. These are the elements which segregate at the grain boundaries, weaken the grain boundaries, and your steel becomes brittle. So my professor thought that is the reason here. And he said, okay, you have to do. When I met him in January 1979, he said, we'll go for OG analysis. And that was the first time I heard that word, OG. I said, what, OG? Could not understand. And even now, you will find people saying it auger. So it is not OJ, it is not auger, it is OG, French. So it took me a few days to understand what he was saying. And then he told me that go to MIT. MIT was 80 miles from University of Connecticut. So I went there, but now the problem. If you put your sample for surface analysis, it will have oxygen, carbon, everything on the surface. And if you want to analyze the grain boundaries, you have to fracture your sample in vacuum, in high vacuum. So there was a special type of sample, small sample having a notch. And this sample will be broken in high vacuum chamber. And then that surface will come in front of the electron beam and you will analyze the composition at the surface. Fun. And this is the surface. See on the right hand side, we have grains. These are grain boundaries. We call it intergranular fracture. On the left, we have different type of fracture. So we are trying to find the composition of these surfaces. And I made many samples. I went to MIT and carried out this. And what I found, there was no impurity on those surfaces. So I had to change the direction of my topic. I had to find the other reasons of embrittlement. See here, you see peaks of copper, aluminum, nickel. These are the main elements. And then oxygen. There's no other element. Even at higher resolution, we don't find antimony, arsenic, bismuth, nothing like that. So my professor was astonished. Said, okay, then find the reason, if this is not the reason. So that is another story, but this was my first experience with OGS spectroscopy. And for few more minutes, I would like to share some of interesting photographs which I have taken on my microscope in the Institute of Space Technology. They will be interesting for you, I hope. And as Professor Grant told, see, when students send their samples for analysis, they will just say, do SAM on this. But that does not mean anything. You have to know what you have to do. So this one student came from Punjab University and had composite of copper with carbon fibers. And this is the fracture surface. And she said, okay, take few photographs at different magnification. That is enough for my thesis. But I was surprised. I noted lines on the surface. And they were actually slip lines. These are very difficult to observe. You have to prepare your sample very, very carefully. But here we could see the slip lines on the surface of the copper. Copper is ductile, okay, slip lines. But at higher magnification, something else was there. Slip lines crossing each other. And that we call cross slip. In material science, we call cross slip. Cross slip is important for high ductility. So this is a very good photograph for the students of material science, that you have evidence of cross lab. You will not see this kind of photographs in any textbook. Now this is another strange photo. When we want to see fine precipitate in our sample, we go to transmission electron microscope. But this photo I got on my scanning electron microscope, very unusual. This was aluminum age hardening alloy. Do you see this? Small this, and then black line. Those black lines are the edges of the disk. You are looking at the edge wise, and then you're looking at this. And this photo is taken at 50,000x. So you see nano size GP zones in SEM, unusual. Then this was a photo we took on our microscope for the resolution test. When you buy a microscope, you check the resolution of your microscope. And you see these are titanium nanoparticles. And the closest distance mentioned here is about 5 nanometers. Even smaller are there, but I can say at least I have a resolution of 5 nanometers. That is the least. And one of my students prepared these silica nanoparticles for super hydrophobic surfaces. They look beautiful, so I have kept in my presentation. And one group was working on zinc oxide nanoparticles. See, this photo is taken at 100,000x. Beautiful photograph at 100,000x. So we have zinc oxide nanoparticles, and these are famous carbon nanotubes, which we usually don't see. And finally, the strongest material, graphene. And we are looking at the edge-wise graphene. And this photo is taken at 150,000x. You require very good field emission microscope for this kind of photographs. Again, this was astonishing for me. In SEM, you get this kind of microstructure. It is very difficult to see. This is spinodal structure. And you have 3 grains, grain boundary, grain junction. And you get spinodal decomposition layers in 3 different directions. Very unusual photograph for SEM. This is high temperature damage of turbine blade aircraft. And you see intergrain fracture. These are the things which disturb us. Grain boundary fracture. And this, my technician, he was very interested in looking at the eyes of the insects. Very strange. These insects have very peculiar eyes. A lot of hexagonal lenses. Beautiful, beautiful eyes. And one group came to me and said, we want to look at the bacteria in yogurt. And they told me we have useful bacteria and we have bad bacteria. Useful bacteria is good for your stomach, and bad bacteria will make your yogurt sour. And she said, this is useful bacteria. So these were the photographs I wanted to share with you, emphasizing the role of vacuum. And in few of the slides, I showed you samples which require lower vacuum. So thanks. Any comment? Again, not difficult question, only comment. Yes. So I was talking on behalf of Institute of Space Technology, which has field emission gun SEM. So we can do wonders if you have some work. Yes, please. So we had heavy lunch. No question. Okay, thank you.
Thank you very much, sir, for your very comprehensive talk. We used to say and even believe that the Safai Nisaf Iman has. Today I found that the cleanliness are also half of the science and technology. So, ladies and gentlemen, in the previous session, our Professor Grant, we discussed like all the process and all the emission spectrums for different elements. Now we'll start again with the polycrystalline effects in Auger electron spectrometry. And I request Professor Grant to teach us this amazing technique for surface analysis.
Change the mouse. Fantastic. Okay, well, welcome back. I'm going to take a seat for a change rather than stand up because I've got quite a few hours to give you over the next 3 days. And I'm recovering from treatment and taking some medicine that makes me tired. So I want to make sure I can keep up my strength for you. Okay. So excuse me for deciding to sit down, but it will help me enormously. Okay, so we're going to continue on talking about Auger electron spectroscopy. It's very interesting to hear about alga and so forth. Just it's amazing, isn't it? The different words that people have for these techniques. And so now I'm going to talk about some of these polycrystalline effects. This example here shows you on the top left here, a secondary electron image. And on the right-hand side is an Auger image. So the electron beam is scanned across part of the surface. And we have these polycrystalline grains here with different orientations. And you can see them in the secondary electron image. But the Auger electrons are also affected by the fact that it's a polycrystalline material. And as I mentioned earlier, the main concern is that the intensities can be different on the different grains. So you can see this grain and this grain have high intensity compared to some of the other grains. Also, you get channeling patterns from the crystals as well. And that can be seen down here, where you have these higher intensities of the Auger electrons coming out from these different grains. A, B, and C are 3 grains, A, B, and C. And these are the intensities of the Auger electrons coming out from those different grains as well. So you get this information about the crystallinity. Here's an early example of studies on single crystals. And you can see here the orientation, the intensity variation is strongly dependent upon the azimuth of the on this particular surface. This is a copper 111 surface, and these are the patterns you get for the Auger signal intensities at different azimuths as a function of the angle of emission. I just want to mention just briefly here also, this Auger transition is MMM. It involves the same shell for all 3 Auger electrons involved. And this is often called a supercosta-Kronig transition. And that's just another term here for a specific case of Auger electron spectroscopy, where we have this involvement of the same shells in the Auger electrons. We normally have MNN, KIL, as I mentioned, LMM, and MNN. But this is an MMM transition, and they are often referred to by this Costa-Kronig designation. And Costa-Kronig transitions, they just use that name because these are extra fast transitions for Auger electron spectroscopy. Distinguish those. Now talk about surface sensitivity. And the electron beam penetrates into the sample, as you've seen. And when the electron beam penetrates, they undergo electron undergoes inelastic and elastic collisions in the material. So when the Auger electrons are produced, and they can be produced near the surface, and they can also produce down into this like inverted balloon that we talked about. But those that are produced near the surface have a high probability or chance of escaping from the surface without losing energy, and therefore will appear in the peak in the spectrum. And those that are produced deeper down in the sample have a chance to lose energy because they're going to scatter perhaps several times before they get out of the surface and go into our spectrum. So the Auger electrons that are produced near the surface go into the peaks. The Auger electrons that lose energy, those that happen to come out of the surface and into our spectrometer, will still be measured, but they have lost energy and they will go into the background. So they appear in the background at lower kinetic energy. So the Auger electrons that appear in the peak are from the surface, and the Auger electrons that appear in the background at lower kinetic energy represent those coming from deeper in a material. And that can be very interesting because if you have a buried layer of a material, the Auger peak intensity can get weaker and the background will get stronger. So that's something a lot of people neglect in doing an analysis, is the intensity of a background associated with a peak. And in Auger spectroscopy and in X-ray photoelectron spectroscopy, this can be very, very useful. And a lot of people don't realize it. As a matter of fact, a colleague of mine that was using an instrument, I was waiting to use it, and they said that the machine's broken because it has a big background associated with the peaks. And I asked what the sample was, and I said, the machine's not broken. That's information about depth. That unusual background is because that particular element is buried. And it turned out they had actually called the company and arranged for a technician to come in to fix the instrument. And if that technician came in to fix the instrument, I'm not sure what would have happened. And I just said to the person, why don't you put in something that you know is going to be give a good spectrum like silver. You can clean it and take a spectrum. I guarantee you the spectrum will be normal. There's nothing wrong with the machine. And they did that and said, you're right. So they had to call up and cancel the visit from the technician to come in and so-called fix the machine. And that was somebody who'd been using Auger spectroscopy for 20 years. And people sometimes just forget about some of these basic principles involved in interpreting spectra. And that's why I go over a lot of these basic principles with you to help you understand about the technique. And you'll see some examples with the electron spectroscopies of the loss peaks, the loss structure intensity, how that can be very useful in the studying the depth distribution of the elements. So the analysis depth is determined by what we call the electron inelastic mean free path. And this is except for a glancing incidence electrons beam, where you have an enhanced surface sensitivity because of the beam being at glancing incidence. But for a normal beam coming in approximately perpendicular to the surface, the analysis depth is determined by this electron inelastic mean free path. So the electron inelastic mean free path, with sometimes abbreviated IMFP, is the average distance electrons travel before they undergo inelastic collisions and therefore lose energy. So elastic collisions are those that change direction but don't change the energy. They're elastic. Inelastic collisions are those that lose energy. So if an electron undergoes an inelastic collision, it's going to have a smaller energy and therefore will not appear in the peak anymore. So this inelastic mean free path, okay, is a very important term in the electron spectroscopies. And it depends upon the kinetic energy of the electron, and it also depends upon the material in which the electron is traveling. And unfortunately, a lot of people forget that it depends upon the material. They think it just depends upon the kinetic energy. And you'll even see books and you'll see software that assumes that it's a kinetic energy of the electron only, but it also depends upon the material in which they're traveling. And we normally abbreviate it by lambda with a subscript I for inelastic. So this is the inelastic mean free path. And here are some examples of inelastic mean free path. On the left-hand side is nickel. And this is in angstrom units, and this is kinetic energy. So you can see here that the inelastic mean free path, except for these very low energies, the inelastic mean free path increases with kinetic energy. So you can see that the higher the kinetic energy, the longer the electrons travel before they lose energy. So they have a bigger chance of getting out of the sample without losing energy and be in the peak. So this is important to remember, that the basically inelastic mean free path changes with the kinetic energy. As a matter of fact, here at this minimum, if the Auger electrons were coming out of the sample at that particular kinetic energy, that's the smallest inelastic mean free path. That would mean that is the shortest analysis depth in a material. And on the right-hand side is a plot of different elements. So at any given energy, you can see different elements have quite different inelastic mean free paths. And this one here is on a log scale. So you can see here quite a variation between the inelastic mean free paths in the materials. And so we just can't use one number. We have to really use it, know what it is for each material if we want to get an accurate measurement of the analysis depth. And that's something we can do in many cases, rather than just say, oh, we're looking at a few atomic layers, or we're looking at a few nanometers. We can calculate out, if we know the material, fairly good number for the analysis depth. So the analysis depth or information depth can be identified as a thickness of a sample, the depth of the sample, from which a specific percentage of the signal originates. And a common number is 95%. So 95% corresponds to 3 times the inelastic mean free path times the cosine of the angle of emission. So if the angle of emission is 0, that means the electrons are coming out perpendicular to the surface. So cosine of theta then would be 1. It's just 3 lambda. So if we know the inelastic mean free path of the electrons in that material, 3 times that number, we can say 95% of the signal is coming from that depth. So for different materials that have different inelastic mean free paths, we can get a good estimate of the analysis depth. So rather than just say it's a few atomic layers, if you know the material, you can actually say 95% of the signal is coming from a certain depth. And there's a nice program that's been written by Sven Tugard, and it's called Quasi's Inelastic Mean Free Path. This just refers to the model was used. And it has a software package, now version 3, that came out in April 2016. And the nice thing about it is free. So he basically adopted a inelastic mean free path measurements, calculations from a database, a standard database. And the database is hard to use. So he decided that he would make this software program. It makes it much, much easier to determine these inelastic mean free paths. And here's the link. to his software. So if you're interested in determining the information depth or inelastic mean-free paths, his software is very useful. It's free, has a lot of elements already put in it, because the calculations of inelastic mean-free path involve many parameters, density and all kinds of things, and he's already put those in for you. So it's a very nice program to have. And I recommend that for you. I just had an email with him yesterday of something else, and he told me he retired this year. And so he told me he reached the age of 72, and he's from Denmark, and he decided to retire. And I replied to him and said, "Oh, you're just a youngster." So I'm 79. So in OJ spectroscopy, we identify the elements by looking for each peak in the spectrum. And what you do is typically start with the most intense peak and identify that. And you might make a guess because peaks overlap. And then you compare the position with a table or a handbook. But the important thing is to look for confirming peaks. So if you have a transition metal, for example, which has multiple peaks, like the LMM set that I showed you that has those 3 bands, they'll have quite a few peaks, and you look for those confirming peaks to confirm the identification. Unfortunately, the software doesn't do that. The software claims, some software claims it looks for confirming peaks, but I know it doesn't because it misidentifies peaks. Another very important thing is to look for the relative intensities, because sometimes you have overlap between the peaks, and that could be an issue. And it's also an issue in OJ spectroscopy, particularly with things like sulfur and molybdenum, because the sulfur peak in OJ spectroscopy, the low energy sulfur peak, overlaps one of the molybdenum peaks almost exactly. So it's very easy to miss the identification of a small concentration of an element because of an overlap issue. It may be possible to look for another peak, a higher energy peak where there's no overlap. But again, you must be understanding what you're trying to solve. But if you don't do a very wide energy range in your analysis, you might misidentify or not see a certain element because of peak overlap. So looking at the peak intensities is also very important. And unfortunately, the software doesn't do that. And you continue this process until all peaks are identified. This is how software should work. Unfortunately, it doesn't really do it. As I mentioned before, hydrogen and helium are not detected because we only have those 1 or 2 electrons in those atoms. Now here's an early example of the application of OJ electron spectroscopy that we can see here. And Dr. Hussain mentioned about grain boundaries and studying them. And this is early work by Hondros and Sia at National Physical Lab in the United Kingdom, where they were looking at this grain boundary enrichment. And basically, there are 2 spectra here, showing you, in the case of the intergranular fractured region, this particular spectrum shown here in full, but up the top here is just a portion of a spectrum over this range here, showing you where the cleavage occurred. And you can see the lack of sulfur in the area that just cleaved. But in the intergranular, in other words, between the grains, you can see the sulfur peak is quite significant compared to the cleavage area. So on those grains, on the surface of those grains, there's a significant amount of sulfur present. And even though the bulk of the iron only contained 44 parts per million of sulfur, in this particular sample, at the grain boundary, the coverage of sulfur was estimated to be about half of a monolayer. So this is about half a monolayer. So significant sulfur segregated, and that could affect the strength and so forth of the materials. So this is a very important application of OJ spectroscopy, using also the high spatial resolution to look at the different grains and so forth in metals. This is an example of sample handling to show you how you must be careful. And this is from a colleague of mine, Joe Geller. He had a silicon wafer, and what he decided to do was blow on it with his breath and do an Auger analysis on it afterwards. And this is what he obtained. So rather than just see silicon and perhaps some oxygen from surface oxide, he also found these other elements present. So that's just from a residual from a breath on a clean silicon wafer. So these techniques, Auger electron spectroscopy and X-ray photoelectron spectroscopy, that I'm going to talk about later tomorrow, are so surface sensitive that we must be very, very careful in sample handling. We definitely can't touch them with our fingers. It's going to contaminate them. We have to be extremely careful because they are so surface sensitive in our analysis. Here's an example of what I mentioned about automatic peak identification. And here's a derivative spectrum, and you can see multiple peaks in here. Well, this software identified carbon, oxygen, and tungsten. And down here, some other tungsten peaks. But it also thinks that there's phosphorus here. There's a peak here, small peak. And down here, there's a small peak. And the software identified phosphorus. And this peak here identified as magnesium. And said this is magnesium down here, like it's a confirming peak. But this is erroneous. If you look at the handbook, or look at a spectrum from pure tungsten, you will find exactly this small peak here, and this peak here, this one here labeled as magnesium, is just the tungsten peak. And this intensity is the correct intensity compared to all the others for just pure tungsten. So the software did not look for confirming peaks. So identifying this as magnesium, if you put that in a report or told a customer that you had magnesium present, they might be scratching their head trying to work out where the magnesium came from. But it's not there. It's just the software is not good enough to do identification. So it's handy to start with, but you need to go through the spectrum and check every peak to make sure they're accurate. And as I said, in many cases, it's not going to give you an accurate composition. Here's another example. This is a silicon piece here, silicon wafer. Here's some high energy silicon peaks. There are also some Auger peaks down here at lower kinetic energy. This is carbon, this is oxygen. You're going to find carbon and oxygen on many materials since it's so surface sensitive. They're not going to have some contamination on them if they've been in air. But see, the software didn't even identify these peaks. And these peaks are obvious, and but it didn't identify them. So by looking at a handbook, you could identify what these peaks are. And it's a set of 3 peaks with some smaller peaks. And this is very typical for that transition set where you have those 3 main peaks, which are the LMM peaks. And this happens to be copper. So there's copper present, but the software didn't identify it. And that happens in a lot of cases. The software won't identify a peak if it is small compared to the others. So you have to go through and do it manually. Now, this software, the manufacturers keep updating their software. It's one way to make money. Some manufacturers charge you for a new version. So they like to give you only certain features. Then the new version comes out and they fix some of the problems. They don't want to fix them all because they want to keep some for later. They want to make you keep buying new versions every couple of years when they come out. But so this software, when they update it to a newer version, the new software, I checked the newer software, and that time it identified those peaks as copper. So that's something that manufacturers sometimes do on purpose, I think, and I don't like it. There are some software companies that give you free upgrades, which I like. So when they improve their software, it costs nothing to buy an improved version of their software. But most manufacturers make a lot of money off their software. And it can be very expensive. This is software from Physical Electronics, And if you buy one copy, it's something close to $10,000. If you want extra copies, it's something like maybe $5,000 a copy. So they make a lot of money off their software. Here's an example also. Remember in that diagram I showed you with different transitions, how you have these bands and how we had those different blue sets of lines. So in the LMM sets, the series transition metals, we have those blue bands, the three main peaks and changing energies. So here are some Auger spectra in the derivative mode of some of these metals: manganese, iron, cobalt, nickel, and copper. And you can see the sets of three peaks are present in all of these spectra, and they change intensities, relative intensities, as we go from one element to the other. And also there are more than three peaks, there are multiple peaks, small peaks as well. But there are three main peaks is a signature for those Auger transitions of those materials. And these are the ones that you would use for peak identification, but you can see you have overlap issues. So if I had manganese and iron, the peaks are going to overlap to some extent. And down here, this region here, these peaks here won't overlap. This happens to actually be the peak of oxygen, but this manganese peak here overlaps a little bit with this one. So you have issues with overlap. And I asked one of my colleagues at a steel company to give me a low alloy steel with a small concentration, less than 1% of manganese in it, because I wanted to see about the how difficult it would be to detect the manganese in that particular steel. So having something less than 1% is not easy to detect. And down here, these low energy peaks, these are the MVV. Remember I told you when you use a V, it means a valence electron. So these peaks overlap even more significantly down here, and would be extremely difficult to use those because of the severe overlap problem you would have for these different metals. Next row, a periodic table. Here's some spectra I took from rhodium, palladium, and so forth. And you can see again, now we've got a different intensities of peaks, different shapes of peaks, and also how they shift as you go to higher atomic number. And you can see the splitting of this doublet also increases as we go to higher atomic number, because the shells are also separating more in binding energy, and the Auger peaks therefore separate more also in kinetic energy when we measure those. Okay, and Dr. Hussain mentioned also about chemical effects. And here's an example of chemical effects in Auger spectroscopy, which can be extremely useful in identifying the chemistry. Here's a spectrum from pure silicon, and there's the silicon KLL spectra, silicon dioxide and silicon nitride. And there's a shift in the kinetic energy of these silicon peaks. And silicon dioxide has a bigger shift, and silicon nitride is somewhere in between. The peak shapes can also change, but there is a chemical shift. And for an oxide, complete oxide, the shift is typically something like 6 electron volts in metal oxides and so forth, and going from pure material to an oxide in Auger electron spectroscopy. Here's an example of line shapes on chemistry, and this is carbon. And here's carbon in the form of graphite. And I mentioned about graphite inclusions in steel versus carbides. And graphite has this very characteristic line shape. It's a very asymmetrical peak. You'll notice that it goes up, but then it goes down much more. So this is a very asymmetrical peak. And remember, this is derivative. So it's basically telling you how the slope is changing. So when the derivative is positive, it means the slope is going up, but not at a very high rate. And when the derivative is big, it's a big, if it's a negative one, it's a big decrease. So this peak is very asymmetrical. And yet in some carbides, here's silicon carbide and molybdenum carbide, And metal carbides are very often this shape, 3 peaks that are fairly symmetrical with a extra asymmetrical peak here on the high energy side. So a lot of the metal carbides have this particular line shape, and this is graphite. So this is very useful to distinguish carbides from graphite in Auger spectroscopy. And in the middle here is the line shape that's characteristic of silicon carbide. So this silicon carbide shape is different from the other two and is very useful to help identify different carbon chemistries. Another problem you can have in Auger spectroscopy, particularly if you're working on aluminum alloys, is that aluminum also has extra peaks compared to what you would normally expect. So this is a spectrum just from a backscattered electron beam. So this is on aluminum, but these are not Auger peaks. This is just the backscattered electron beam using a 1,000 electron volt beam. And you can see here these extra peaks in the loss region. We call this the energy loss region, where the electrons have lost the energy from scattering mechanisms. And some are labeled B, and these represent what we call bulk plasmons. So in a free electron-like material, like aluminum, we can excite these plasmons, and they will have specific energies, and they're quantized. So we have the specific energy loss, and this is called the first order plasmon, second order plasmon, third order plasmon, fourth and fifth, and so on. And they get weaker in intensity as you go away from this main peak. So the series of peaks are equally separated because you're exciting these plasmons in the bulk of the material. These electrons that are present in the free electron-like material can take energy away from that Auger electron that's been produced. You can also get plasmons from the surface, which I've labeled here as S. Now, there are books written on plasmons. Okay, it's a big field. But in Auger spectroscopy, it's important to be aware of the fact that these can occur. So if I have an Auger spectrum of aluminum, the peaks aren't going to be as sharp as that backscatter spectrum I showed you. It's more like this. So here is one of the Auger peaks. This is a KL23L23 peak of aluminum. And this one here is a KL1L23 peak of aluminum. And the extra peaks are not Auger peaks, they're plasmon peaks. So this is the first bulk plasmon, second order bulk plasmon. This is the first order bulk plasmon from this particular Auger peak. And you can see they're equally spaced and they decrease in intensity. So you've taken away intensity from this Auger peak and put them into these plasmons. So that's something that's important to realize. And if you look at the Auger spectrum, if I'm working with aluminum and I see these plasmons, I know I don't have a complete oxidation. I mean, I have some free electron like aluminum. It was aluminum metal. If I had aluminum oxide, it's an insulator. It's not a free electron like material. So aluminum oxide would show me no plasmons. I would not see any plasmon peaks, and I would know, therefore, it's not metallic at all. Here's an example from Paul Palmberg early on, showing you here's an elastic peak, backscatter elastic peak with the plasmons. This is a case of magnesium metal. And over here is the Auger spectrum from magnesium metal. And it has these ones here that identify with numbers are the Auger peaks. And the extra peaks are the plasmon peaks. And when you oxidize the magnesium, this is magnesium oxide up here, you can see that the peak shifted, and it's shifted by about 5 electron volts. And you also see the lack of plasmon peaks. There are no plasmon peaks involved. So that's another key to understand chemistry. But of course, we have other peaks in the spectrum. Here we see oxygen, so we know it's aluminum oxide, magnesium oxide. So we can tell what particular compound is. So those that don't have plasmons we can identify what it is based on the other peaks that are present in the spectrum. So it's something you can observe. Unfortunately, the software sometimes thinks the plasmons are different elements, and therefore you have something else, but it's not. It's a plasmon. And you'll think the programmers would say, okay, I got aluminum, look for plasmon peaks. They know where they are at a certain energy and see if they're there. But the software doesn't do that, unfortunately. So again, you must be careful in doing an analysis to realize that these peaks can be there, in these free electron-like materials. The instrumentation. This is a photograph of one of the earlier instruments, scanning Auger microprobe. And this is the main ultra-high vacuum chamber here. And this is an instrument made by Physical Electronics, which we call PHI, Physical Electronics. And over here, this is their secondary electron detector. And their Auger instruments are based on a special kind of analyzer for measuring the Auger kinetic energies, electron kinetic energies. And shown here on the right, it's called a cylindrical mirror analyzer. So they have an outer cylinder and an inner cylinder. So the outer cylinder is this one. This is one side of the outer cylinder. And this is the inner cylinder. So it's one cylinder inside another. And the inner cylinder is at ground. And there are apertures on the inner cylinder. So when the electron beam excites Auger electrons from the sample, some of those will go in through this entrance slit. And by putting a negative potential on the outer cylinder, the electrons will be bent around and come out through this exit here and this exit aperture and go into our electron detector to measure our spectrum. So you obtain a spectrum by changing the potential on this outer cylinder to bend around electrons that have changing kinetic energies. So if you put a higher negative potential on here, that means that the electrons that are traveling through this path will have a higher kinetic energy. So that's how we obtain a spectrum. Another feature of the physical electronics instruments is that they incorporate their electron gun inside their analyzer. So they call that gun a coaxial electron gun because it's coaxial on the same axis as the analyzer. So they put their electron gun inside the analyzer. So here's their emitter, and they have their various focusing elements and so forth, and the beam comes out and strikes the sample. So that's their philosophy. That's how they make their instruments. Other manufacturers will have an external electron gun and perhaps use a different type of analyzer as well. There are different types of analyzers that are used for Auger spectroscopy, but this is the type that's used by physical electronics to take Auger spectra. And the electrons that come out the back here are multiplied by what we call electron multiplier, and then we get our signal. So we scan this negative potential on the outer cylinder to measure the different energies of the electrons coming off the sample to give us our spectrum. And all that, this part here, is contained in this region here. And the earlier PHI instruments used tungsten filaments, just as Dr. Hussain mentioned, about different filaments, later used lanthanum hexaboride, the lab 6 that he had in his slide, to increase the brightness so you get better, more current into a certain spot size, and later to field emission, so you can get even higher spatial resolution. And in the field emission sources, they have an iron pump up here to keep that clean. As he mentioned also, it's very important to keep that emitter clean. Just a little bit of electron optics. If you want to increase your spatial resolution or change your beam current, get more beam current, to get a better signal to noise in your spectrum, this kind of a plot tells you a lot about how the electrons work in an electron gun. So this is beam diameter, and this is on logarithmic scale. And this is beam current, also on logarithmic scale. And here, 4 different beam voltages that we use in their instrument. So if you start off with 3 kV beam voltage, that's the blue one, that's the one at the top. So you can see at a certain beam current, you get a certain spatial resolution, beam diameter. If you go to higher beam energies, 5, 10, and 20, you can see that for the same beam current, you're going to get better spatial resolution. So this kind of a plot shows you the interaction between the beam energy, and the spatial resolution, the size of your electron beam out of the electron gun. But remember, you get scattering in your sample, so the area analyzed can be bigger than the electron beam size that you're using because of scattering. At what time am I supposed to finish? Uh, 4 o'clock. Is that right? 4 o'clock? Yeah, okay, thank you. Another thing is that 2 companies have made these small Auger instrument attachments. So rather than spend $1 million or more, $2 million to buy an Auger instrument, some companies, RBD Instruments, based in Oregon in the USA, and Stibe Instruments, which is really a German company, but has their facility also in the United States, designed these 2 small instruments. And they're both on 2 3/4 inch OD complat flanges. Complat flanges are the ones that use copper gaskets. They keep a good vacuum, easy to seal, keep ultra high vacuum. And you can see here on the left-hand side, one by RBD, very simple Auger electron system. This is the whole thing. So there's an electron gun inside. Remember, this is 2 3/4 inches across here on this flange on the outside. So it's a coaxial electron gun at 3 keV beam energy. It only has 150 micrometer beam diameter, and it doesn't have any scanning capability. So you can't do imaging unless you move the sample. And it's a single pass cylindrical mirror analyzer for analysis, just like I showed you of what PHI uses. So this is mounted on a system and self-contained. It has its own electron gun built in. It has the analyzer, everything built in. And there's a bellows here so that you can move this analyzer, electron gun analyzer, in close to a sample to do an analysis. And then Stibe Instruments is also designed an Auger detector, but it doesn't have electron gun built in. It's designed for those systems that grow MBE, molecular beam epitaxy, where you're growing layers of elements at a time. And on those systems, you're typically going to have an electron gun that's used in conjunction with reflection high energy electron diffraction for looking at the growth. So you already have an electron gun on those systems. So what he did was design a Auger probe. So in here's the detector and analyzer for measuring the Auger spectrum. And one nice thing about this is it's designed to work in growth chambers. Now, many of you are interested in growing films, and the vacuum is not ultra high vacuum. And that can be a problem with detectors and so forth. And he designed this particular probe to work in growth chambers and so forth. And also has a long working distance, so it doesn't have to be down close to the sample. And but it works with an existing electron gun, and normally one of these reflection high energy electron diffraction guns, typically used in molecular beam epitaxy growth. Back in the early 70s, we made our own analyzers, and I started using in the 60s. I used retarding grids, which were used for electron diffraction studies, and we could do Auger electron spectroscopy in those. And then we built our own cylindrical mirror analyzer, and it worked very well. Then later, physical electronics came out with commercial instruments, and using also the cylindrical mirror analyzer. That analyzer was developed long before that, and all the conditions and focusing properties were all well established for those analyzers. And they're quite good analyzers. Here's an example. So here's a small vacuum chamber. This is the RBD instrument. This is the electron gun and analyzer on this flange. And is an example of a spectrum here from silver, and down here from copper, with that particular very simple Auger attachment to do Auger work. And they call it a micro CMA, is what they call it. And so that's just that little attachment on there. This slide here is only of great interest if you have instrumentation and you want to calibrate your energy scale of your instrument. So if your energy scale is not calibrated, you could have wrong energies for your peaks. So this is an ISO calibration table that the ISO, the International Organization for Standardization, has adopted for calibration of instruments. So I'm not going to go into detail on this, but basically we have a calibration way for our Auger instruments. Early on, different manufacturers calibrated in different ways. And now we have a way to do it exactly. Vacuum system, okay. And as previous speakers have mentioned, particularly Dr. Hussain, about the different kinds of vacuum chambers and so forth. We use ultra-high vacuum, 10 to the minus 9, 10 to the minus 10 torr, very similar to millibars. And we use ion pumps for the main chamber. Also, sometimes we use what's called a titanium sublimation pump, and that's a very active surface you create, titanium film, for absorbing hydrogen. And you also have an extra ion pump if you have a field emission electron source to keep that very clean, as Dr. Hussain mentioned also. And we normally use a turbomolecular pump, of course, with a backing pump for evacuating the load lock. So we normally put samples in through a load lock. We put them into a part that comes up to like dry nitrogen, like you mentioned. And then we pump out that section, open up a gate valve, push the sample into our main analysis chamber, and try to keep the analysis chamber ultra-high vacuum, keep it clean all the time. And the systems are bakeable to improve the vacuum. So to improve the vacuum, you basically take off all the cables and heat up the whole chamber to typically maybe 150 Celsius for several hours, typically say overnight. When you come in the morning, it's cooled down and you'll get a much better vacuum. So you dissolved a lot of gases, water vapor and things off the walls of the chambers. And when it cools down, you'll have a much better ultimate vacuum. So to get ultra high vacuum, you have to bake your systems. And like I mentioned, for Auger spectroscopy, you typically bake them for about 6 hours, something like that. It's adequate. Those people that work in molecular beam epitaxy will typically bake their systems for 7 days at a higher temperature, because they need really good vacuum, much better than what we normally use, because they don't want any kind of traces of oxygen residuals and things like that in there that will affect their growth and properties of their films that they're growing. So the vacuum system is extremely important. We have to have a vacuum, of course, to electrons to move because they have a limited path in depending upon the pressure in which they travel. And ultra high vacuum also is good because it'll keep your sample clean. So if you fracture a still sample inside your system and then you analyze it, it's not going to contaminate before you do your analysis. So ultra high vacuum systems are essential for doing Auger electron spectroscopy. Those kind of cases, except for when you're growing films, like I mentioned for the case of MVE, where you have that stibe attachment, which is designed to work in different vacuum. But that comes because of the vapors present from the films that you're using, the elements you're using to grow those films. The samples have to be vacuum compatible. And as I mentioned, they're inserted using a load lock. That means that we keep our analysis chamber very clean and only expose a region beyond what we call load lock to atmospheric pressure, and again, to a clean gas. The size of samples, it depends on the manufacturer. A lot of manufacturers, through the load lock, they don't use big load locks. So you're limited in size. Also, when you put the sample in, the manipulator is limited also in translational size. So typically, we only can move samples around by several centimeters. That's the limit. There are some manufacturers of instruments that allow 12-inch wafers to be measured. And that's in XPS, special manipulator to allow a 12-inch wafer to be analyzed and so forth, XPS. But for most instruments, the size of the samples is a factor. So if you're buying an instrument, then that's an important consideration to make. And the sample movement you want, the translation, rotation, and tilt are different things that you would like to have. Translation to look at different places, because the electron beam coming out of the column can only scan a certain area, which is fairly small. So if you want to look at something that's millimeters away, you have to move the sample. Rotation is useful, and I'll show you later how rotation can be very useful when you're depth profiling. And tilt, again, to change the surface sensitivity by changing the tilt on the sample. These are different things that are nice to have. You need a stable electron beam position on the sample. Unfortunately, some of the instruments with time, with temperature during the day, the electron beam can drift a little bit in relation to your sample. So at higher magnifications, your image is going to shift a little bit. And some of the manufacturers use this image registration. So if you're taking data and making a map or an image, they periodically check to see if the beam has moved in relation to the sample, and if so, to make that correction. And they call that image registration, just to correct for any drift during the time of taking a map. Heating and cooling, you can have that in situ. You can heat up a sample or cool it down inside your analysis chamber. So if you want to look at diffusion on materials, you can do that in situ. If you're looking at insulators, charge control is an issue. And sometimes you might like what's called a preparation chamber. So you can do things outside your analysis chamber where you could expose a sample to noxious gases and things like that you don't want to put inside your analysis chamber. So you can have that preparation chamber where you can do certain things as well. Or you might want to heat up the sample out there or do a reaction with oxygen or something like that, and then put it back into your analysis chamber. But you don't want it passing through air, otherwise it will contaminate your sample and affect your analysis. So preparation chambers are also very useful. And scanning in Auger spectroscopy, here's just a crude example of a scanning electron microscope to show you what you are doing, electron gun. And then you have all these different lenses and astigmatism correction and things like that, and scanning elements to move the electron beam around your specimen to get your secondary electron image or a backscattered image, depending upon what kind of detectors you have. And you can have X-ray detectors, and you can also measure the specimen current to ground, different ways for imaging your sample. So in Auger electron spectroscopy, in many instruments, we can also move the electron beam over a limited area and do Auger mapping. And here's an example. On the left-hand side is what we call Auger line scan, and this is the gallium signal, and this is distance in nanometers. So this is 0 to 200 nanometers. And this is the gallium Auger line scan, showing the intensity of the gallium Auger peak. And over the right-hand side is a map of gallium. And this is a sample that contains gallium arsenide and aluminum arsenide. So we have regions of gallium arsenide sandwiched between aluminum arsenide. And by looking at the gallium peak, we can see the presence of the gallium. So the gallium over here in the gallium arsenide is the deeper color here, the brighter color, the orange color. And then it drops off in intensity. And this will be in the aluminum arsenide, and then goes back up again when we go into the gallium arsenide layer and so forth. So just a few things to mention here. This kind of a material can be used as a reference material to check our resolution of our instrument. But you'll notice also that the peaks, the intensity of the gallium doesn't go to 0. So these are 10 nanometer. Okay, this is 10 nanometer region here between these different layers. And you can also recall this as superlattice, 10 nanometer regions. And even though these layers are 10 nanometers in thickness, and our beam can be smaller than that, the ballooning issue I told you about before means that the backscattering and so forth is going to give you a signal even when the electron beam is not hitting that region. So you can see the gallium signals does not go down to 0. And that's because of scattering of the electron beam in the sample. Another thing to note here is the time. This line scan took 2 minutes, and the map took 200 minutes, 100 times longer, because you're taking essentially many line scans, if you want to look at it that way. And in my career, I didn't do mapping, really. Mapping takes a long time, and I prefer to do line scans. So by scanning electron beam across the different materials here, I get useful information. And the map doesn't give me really much more information at all. It just shows you that the regions here, these layers are fairly uniform. Now, of course, if you had something that was not uniform, the map might be useful. But I find that the mapping is not normally needed. It's something that's nice in reports, and something that's very useful to sell instruments. If you have nice maps in your brochure, the customer will say, oh, that's a nice instrument. Okay, if you show something like this, they'll say, oh, that looks pretty ugly. I don't think I'd want to buy your instrument. It doesn't look like it's very good. So, but in really analysis of materials, it again depends on what you're doing. Now, if you have quite a non-homogeneous surface, though, say you have a fracture. So you've fractured a material. And in the secondary electron image, you can see it's quite different. It's very non-uniform. So there, a map could be very useful because you have a lot of different regions. And therefore, in some cases, it is very useful. In this case, it's a superlattice that's been grown by molecular beam ecliptaxy, and we know that the growth is very good. So we wouldn't expect any non-uniformities. But if the image shows you a lot of non-uniformity, mapping would be very useful in those cases. So there are some cases where it can be very useful, but again, remember, it takes a lot more time to do a map. Of course, you can also do multiple point analyses by looking at specific places and taking point analyses rather than a map. Here's an example, simple example of scanning Auger microscopy. And sometimes we use the acronym SAM for scanning Auger microscopy, looking at some defects in aluminum metallization. So on the left-hand side here, this is the SCM image you get when you're scanning electron beam. So our Auger instruments has a secondary electron detector for getting this SCM type image. And down here are the conditions. They use a 20 keV beam. And this is 100,000 times magnification. And the bar marker is very important to show you the spatial distances on your image. And you can see here, you've got these different regions. We have much higher intensity on these three regions here compared to the background. So it's very likely that these three regions here might have a different composition. And what I typically do is to take an Auger spectrum off these regions, point analyses of this region, that region, and that region, and then a few point analyses at different places around the background to see what we get, check for uniformity. On the right-hand side is an example of a map. And this is, shows you this is aluminum, remember? So this blue region here, this is aluminum, and the red regions here represent copper. So copper is detected here in these red regions. So this is copper, basically inclusions here, or copper defects in that aluminum metallization. So the Auger spectroscopy is very useful for identifying what these particular regions here are. So if you're growing a film, you often have problems deciding on the conditions of growth, and the SEM can tell you the uniformity, the flatness, whether it's constant intensity. But when you have particles, you'd like to know what the composition of the particles is. And in SEM, you might have access to EDS. And I'll show you later that EDS doesn't always identify the particles correctly because it's more of a bulk technique, because you're looking at the X-rays coming out of the sample, out of that inverted balloon. And Auger spectroscopy will really get you the information about that particular particle. So I'll show you that shortly. But so combination of the SEM and Auger imaging is very useful for your analysis. Here's another example. This is a precipitated steel. So we have iron here, largely iron. And this yellow box here is expanded into this lower left-hand image. So you see the little particle in there inside the yellow box is now this particle. And over here are overlaying maps. So you can, in the software, you can overlay maps. So you take a map of iron, and the map of iron is in blue, and titanium and carbon here. Titanium is in green and carbon is in red. So you can see in this case, the titanium and carbon are overlapping because you're getting yellow. Because titanium in green and carbon in red, if they're both present, will give you this yellow color. Now, of course, I could just take, again, I could take point analyses on this particular precipitate, a couple of different places, and take some on the background region here, and then look at my whole spectrum. And I would get the total composition. And again, this map, in my opinion, maybe not very useful, just takes more time to acquire and doesn't really provide me any more information than I would get by just taking point analyses at different places. And the point analyses are much faster, and you'll get the complete composition in the material as well. But here's an example where mapping is very important. And this is a case of different phases in aluminum alloy. Over here, this is the basically aluminum alloy. And you can see on this particular image, on this particular surface, you can see various features. And it's quite possible that these features here might be different composition. They might be, you know, these different phases in the alloy. So what we'd like to do is to analyze these different regions here. And as I mentioned, we can take point analyses on these and see what the composition at these different points and background and so forth, and see what we have. And you have to do that initially anyway, pretty well, to see what elements you want to map. You're going to take a map. And on the right-hand side, up the top here, are 3 elements that in overlay format that we have. We have aluminum in blue, and you can see that's basically the main part of the alloy. It's aluminum alloy. Copper is in green. That's this region here. Manganese, okay, is in red. So if we go back over here and look at it, okay, we have our iron. This region here, it looks rather rough. Here, you can see it has a high composition of copper. And these particular features here have manganese. But you'll notice in the map on the right-hand side that there's a black region here. So this region here doesn't have any of those 3 elements present. So something else is present there. So after you take these maps, you would go back and do a point analysis there and see what other elements might be present in those particular places. And then you could, if you want to do a map, including other elements, this is a map then of magnesium and silicon, as well as the manganese. And the magnesium is in green and silicon is in red. So you can see there's magnesium present in here, where we had some of the copper. We have magnesium as well. And also over here, we have some magnesium in green. And then we also have some of these yellow regions, which are combinations of magnesium and silicon here as well. So this is a case where mapping can be quite useful for looking at these different phases in that particular alloy. But again, you know, maps take some time. But, you know, if you're going to do mapping, you can always do it overnight. You can set up the instrument to take maps overnight. You don't have to be present. Okay, it'll do image registration for you if you need it. Point analyses while you're there, you can do those to see what's going on and set up your map so you can take that, like I said, overnight and save a lot of work time. Okay. We're supposed to finish in a couple of seconds. Is that right? Okay. Let me see what I got next. Okay. This is one more slide, and just shows you a combination of spatial resolution, beam energy, and beam current. And this is a plot here that from JOL. JOL is a well-known manufacturer of SEMs, and they also make Auger instruments as well. And it shows you what we talked about a little bit. If you go to higher beam energies, you get better spatial resolution for the same beam current. So this is a 1 nanoamp beam current at 10 kV, 20 kV, and 30 kV. And you can see how the spatial resolution improves as we go to the higher beam energies. Now, if we go to higher beam currents, we want more signal maybe in our Auger spectrum, get better signal to noise. You can see as you go to higher beam currents, the spatial resolution degrades for a given beam voltage, beam energy. And that relates back to that graph I showed you earlier, how these all interact. And at 10 nanoamps, If you go to higher beam energies, again, the spatial resolution improves. This is far superior to this one at 10 kV. And if you compare them now across here at 30 kV, this is excellent resolution, but only 1 nanoamp. And you can see here that a compromise might be something like this for doing Auger spectroscopy, where you'd like a beam current maybe of a fewer nanoamps, that you might select this condition, 30 kV, and then maybe 4 nanoamp beam to get a reasonable spatial resolution and also a reasonable Auger signal. So this is something you do by trial and error to decide what kind of spatial resolution you want and how much time you can spend to acquire your Auger spectrum or your Auger map. So they all interact. The beam energy, the beam current, and the spatial resolution all interact. So you have to compromise between these different settings in your instrument. Okay, so this is a very good place to finish up for the day. I hope you've learned a fair bit about Auger spectroscopy. I've got a little bit more about Auger spectroscopy tomorrow. And then we'll start talking about X-ray photoelectron spectroscopy as well tomorrow. Okay, so thank you for hanging in there, as we say, and see you tomorrow. Yeah, question.
For example, 1 nanoampere current is better than, in my opinion, than 2 nanoampere, 4 nanoampere. So 1 nanoampere, so the lower current is better, and the higher amount of current, so it is difficult to, because the electron itself, higher the current, then we will have.
Yeah, it's part of the optics, electron optics, that when you go to a higher beam current, you're not going to get a good spatial resolution. And also when you go to higher beam voltage or beam energy, you get a better spatial resolution. That's just the electron beam optics. But this particular figure I'm using is to show you how the current, the beam current and the beam energies interact. And to take an Auger spectrum, if you take it at 1 nanoamp, you can still take an Auger spectrum, but you'll get much better signal to noise if you use 4 nanoamps.
Yes.
So this illustrates that if you want the best spatial resolution, you have to use small beam current and high beam energies, like bottom left. Okay.
Yes.
If I need more intensity in my Auger current, I'm going to have to compromise and get a bigger beam current. And when I get a bigger beam current, I'm going to lose some spatial resolution. But it's not going to be a factor because I still know that basically this is what my sample looks like. And even though it's a bit blurred here, I still know what it really looks like under high resolution. I can even go to 10 nanoamps because I know that this really can be sharpened up to that.
So can particularly you can tell how much Auger signal is related to these current, because this current is from electron beam from the gun, right? Here on the slide, and how much the signal, Auger signal, also related with these current.
Right. How big is the signal? Well, you can still acquire the Auger signal, but the Auger signal, if this is the beam current and you go to 10 times the beam current, you're going to get 10 times bigger Auger signal. So the signal to noise goes to square root. So at 10 nanoamps, I'm going to get approximately 3 times better signal to noise. which means I'd get the same information in a third the time. So it's a compromise of time is what you want. You can definitely take the Auger spectra here, no question. But it's a matter of time. How much time do you want to spend taking your spectrum? And if you're have your own instrument, then you can spend as much time as you want. But if you're outside and you're paying somebody to do your analysis, and this one takes 10 times longer than this one, you're going to pay 10 times more money to have analysis done than this one. So that's where it really comes into play.
Thank you.
Thank you very much, sir, for such a nice comprehensive talk on our electron microscopy. So this is the end of our technical session, and tomorrow we will meet again in the morning at 9. Please follow the timeline. Thank you very much.
Yeah, thank you.